Doing great. Um, and before we get started, I would just like to remind everybody about our code of conduct. This is a friendly space. When you talk with one another, just be kind. We're all here to learn from one another, so there's no stupid questions. We value new ideas, encourage innovation. We'd like to share the air so that not one single person is always talking. Please show appreciation, acknowledge teamwork, offer constructive feedback, and listen and try to understand. Um, Also, I would like to acknowledge all of the effort that's been done to make this meeting possible. So this is the administrative and multimedia team that made it happen. For people who are here and online, you've seen Teresa and Kaylin this morning. But from time to time, you'll see Paul, who's just arriving, actually. But behind the scene, Elizabeth, Daniel, and Kayla also did a lot of work to make this happen. So thank you very much. You all have access to this agenda. And for this morning, Kate is going to monitor the session, try to keep us on time. Everybody has an allocated slot of about 20 minutes. So please try to leave 2 or 3 minutes time at the end of your talk for questions, if you can. And without further ado, Kate, I will let you introduce the next speaker. Oh, and for speakers that are online or in here, if you have sent your presentation, I can present it for you, or you're more than welcome to share your screen and present your talk. So, Michele, you let us know what you prefer to do.
Yeah, okay. I'd rather share my screen.
Okay, go ahead then.
Yep. All right, first up is Michele Petrini with the topography constrained tipping point for complete Greenland ice sheet melt. He'll be a remote speaker this morning.
Yes, just 1 second, because seems I cannot share the screen because of my computer. Okay. Okay, now maybe it's, oh no. Okay.
Well, and already this morning, once I joined without clicking the companion mode. So if you're joining from in here, please use companion mode because it was loud and annoying.
Sorry, companion mode, is this people? Okay.
Yeah, it should be a link when you the first screen.
Join Google Meet. Yeah, to do it. Okay, I'm gonna try again.
Okay, I might need to quit and reopen. Sorry, I'm really sorry about this. But,
Thank you.
It
gives a couple of minutes for people to grab a cup of tea, coffee, or snacks.
Okay. Sorry about that.
There's a lot of snacks in there. Help yourself.
You cannot eat until it's gone.
Frank.
So I told him. All right, Michele, would you like us to just present your slides for you? Oh, you're muted.
Sorry, I'm just doing one last attempt because the problem is the recording, apparently, not the sharing itself. Yeah, so if you can just use my slides, that'll be better. And you have a keynote. I sent a keynote by email, and if you could open that, that would be better because there are videos in it.
this is what I have. Is it okay to share this?
Yeah, that's the PDF. Do you have the keynote too?
Um,
Tim, companion mode's just for people in the room.
no, I do not have the keynote.
Okay, okay. Well, I can go with the PDF, and then well, we'll see what happened with the video. Maybe I can send them to. Well, I'll just start to not take more time. So yes, I'm gonna talk today about this study that is currently in review for the cryosphere, and I'm gonna like show you some results about this study looking at the long-term evolution of the Greenland ice sheet. And so just to start, next one, please. So what we are interested in and what we know about this for the long-term evolution of the Greenland ice sheet. Next, please. And our goal is to mainly look and identify thresholds in surface mass balance (SMB) for complete Greenland ice sheet melt, and in particular if there are any tipping point associated to this threshold. So basically threshold for significant change. So we don't look here at reversibility or multi-stability, just rather at if there is any nonlinear response of the Greenland ice sheet to the SMB forcing. And we also look at the processes controlling the thresholds, patterns, and timescales for a Greenland ice sheet melt. And next, please. So what we know, I mean, previous studies that look into that, it is a little bit conflicting because Robinson et al. And also Leverman et al. 2013 found this very sharp threshold behavior for the Greenland ice complete melt. But a more recent study, coupling an intermediate complexity or system model to an ice sheet model, Gregory et al. 2020, found actually a wide range of equilibrium states. So there is it's not clear which one of the two it might be. And in general, like all these studies tend to agree on the global mean temperature threshold for Greenland ice sheet complete melt between 2.2 and 3.2 Kelvin. And another thing that I think is useful for what I'm showing today is that during the last interglacial, the Eemian, this threshold for complete melt was very likely not passed, and so only a small portion of the ice sheet was lost. Next, thank you. And for the methods now, next, please. We are our starting point. So we are using the community ice sheet model in this study, and our starting point is actually a fully coupled simulation. So we use, thanks to the new capability of the community Earth system model, CESM, the coupling with the Greenland ice sheet component in CESM. We have an advanced SMB calculation and downscaling, and so we start from a fully coupled simulation of the global climate and Greenland ice sheet published by Montier et al. 2020, and this is a 4 times CO2 simulation. And in this simulation, next please. In this simulation, the CO2 is increased by 1% until reaching 4 times pre-industrial value. And we select from this run, and you can see a little bit of a diagram in the figure, multiple time intervals that are corresponding to different levels of SMB or global mean temperature. And basically, each time interval that we select is containing a climatology. So in our case, 23 years of SMB forcing at multiple elevation classes. And that's very important for us. So we use each SMB interval to force the community ice sheet model CESM, basically cycling the SMB forcing over and over until we reach either Greenland ice sheet equilibrium or deglaciation. And why this is important that we have SMB at multiple elevation classes? Next, please. It is important because it basically allows us to account for changes in geometry, in ice sheet geometry, and we basically update the surface mass balance throughout the simulation. So the SMB is calculated in CESM, at these multiple elevation classes using downscaling of surface air temperature. And so basically, when we force CESM, we force with Kappa history files that contains SMB at 10 different virtual elevation. And you can see in the figure on the left, the 10 basically elevation beams. And so as the ice topography is evolving, the SMB is basically corrected, adjusted for these changes. Next, please. So all these accounts allows us to account for the surface for the SMB height feedback, and I'm going to show you some results. The first part focusing on the SMB threshold, and you can see in this slide first that we actually find a positive, so larger than 0 SMB threshold for Greenland ice sheet deglaciation. And at the end of our simulation, we mainly have only 3 main final states of the ice sheet. We have either more than 80% mass or ice volume remaining, and that's for an SMB larger than 317 gigatons per year. This is integrated SMB over the ice sheet. Then we have a 50% state for an SMB forcing between 286 and 255 gigatons per year, or we have less than 20% volume remaining for an SMB lower than 230 gigatons per year. So you can see that it is a quite sharp threshold. And if you can now go to the next slide, please, you can see in the figure on the left, I am plotting the initial SMB forcing on the x-axis and the final Greenland ice sheet volume on the y-axis. And you can see that the jump from 50% and 20% volume is actually happening for a very small perturbation of the SMB forcing. So this is when I was talking about this tipping point behavior, that's what I was meaning, that we have a very nonlinear response for a small change in SMB forcing. And this SMB threshold is positive and corresponds to around 60% decrease in SMB from the pre-industrial value. And I'm talking about here the CESM pre-industrial SMB value. And the first tipping run corresponds also to a warming than a pre-industrial of 3.4 Kelvin. So this is not very far from other estimates in previous studies. And you can see also in the other figure here on the right the time series for the X volume, and you can see on the x-axis the time scale in thousands of years. So the first run to tip is taking 40,000 years to completely melt the Greenland ice sheet. And then for high forcing, of course, the time scale is reducing. Now, if you can go to the next, please. I'm talking about a positive SMB threshold, and I'm talking here about the initial SMB. But we can see, looking at the simulation, that the first run to tip is actually the first run where the SMB at some point becomes negative and remains negative for at least 5,000 years. And that's basically the first green run on the plot. And you can look at the integrated SMB in the lower panel, and you can see how the SMB is becoming negative and staying negative. And this is the first run that is basically yielding less than 20% volume. And if you would go now to the next, please. And you can see also that the ice sheet volume curves are really not flat at the end. There are some wobbles here and there. And basically, in our simulation, the ice sheet never really reach full equilibrium when it's close to the SMB threshold, because there are some oscillations. These are, we checked over longer time scale, basically quasi-periodic oscillations. And this is happening because of the SMB height feedback. So in our simulation, it's not only a positive feedback, because it's responding on the one hand to ice thinning due to surface melt, and then in this direction, the SMB height feedback is a positive feedback, because the SMB is becoming smaller, and so there is more melt and so on. But on the other hand, there is bedrock uplift because of the isostatic adjustment. So GIA. So when the bedrock is uplifting, the SMB is becoming larger, and so this is basically counteracting the the effect of surface melt and the positive feedback. And that's why in some cases we have these oscillations because the margin is retreating, then there is a bedrock uplift, and then is re-advancing. And you can see in the three maps in the figures for three selected runs, that's the where the oscillation is happening, and that's the gray area in the figures. Now, if you would go to the next, please. I'm showing also an ice volume curve for basically some of the same simulation without isostasy. And you can see these are the dashed lines in the bottom panel. And you can see that when J is not included, Greenland ice sheet complete melt is happening for much lower SMB and global mean temperature thresholds. Next, please. Now the second part of the results. So the topographic control on the SMB threshold. So if you now go to the next slide, we go back for a moment to the free plots, so the free main final state, and we look at where the ice is the acid is retreating. So in the more than 80% final volume, we can see that retreat is very limited to the southwestern margin, whereas in the 50% volume, the retreat is actually occurring at the southwestern, but also at the northern margin. And what is happening here is that the central western margin remains close to the coast. And then in the less than 20% volume, the ice is remaining only at the eastern margin. And there are some isolated ice caps in the south and in the north. So the question here is what is happening between the 50% and the 20% volume? So how does this transition occur? And now I'm really sorry because I have two videos in the next two slides which are not playing on the PDF. Now, if you would just go to the next slide, please. So I can tell you what the video will basically show. This is basically the last run before tipping. And what is happening is that in this run, the central western margin remains quite close to the coast and eventually reconnects after this oscillation and re-advance. And I highlighted with a red circle the area where there is a topographic high in the central west. And that's basically the region where the ice sheet tends to be closer to. And if you would just go to the next slide now. What is happening then in the first run that is tipping, the 3.4 Kelvin run, is that after 20,000 years, basically the margin, the central western margin is cannot re-advance anymore close to the coast and is going all the way to the east. And that's basically when the tipping point is passed and there is this runaway retreat. So our question here, our hypothesis is the central western margin, is it a predictor for long-term substantial ice loss? And if you go now to the next, please. And what we did to test this hypothesis, we basically repeated this tipping run, plus 3.4, and we basically inhibited the SMB height feedback in the red region. So in this region of high topography, and it's basically the red box in the upper panel on the left. And so you can see the third panel is the standard 3.4 run, and the last panel on the right is the 3.4 run when we basically inhibit SMB height feedback only in that square. And you can see that this run is not tipping anymore. So we apply a local, basically a local constraint on the topography inside the red box, and we actually have a much larger scale effect. And basically the ice volume is very close to 50%. And if you look on the right at the time series, is basically the green line that is around 50% volume. And so it's basically behaving very similar to the 3.2 Kelvin run. That's not tipping at all. And also in the 3.6 Kelvin run, that was basically deglaciating faster. The ice volume remaining, applying the same constraint to the central western margin, is around 40 and 50%. Now, if you go to the next slide, please. I just wanted also to show somehow a teleanalog. So the map that you can see on the left is absolutely not my work. Is from a run last interglacial fully coupled simulation with CESM of the last interglacial by Sommers et al. 2021. I just wanted to show that for basically the minimum volume or the minimal extent of the Greenland ice sheet around 122,000 years ago in this run is very, very similar to the basically pre-tipping ice sheet configuration in the 3.2 Kelvin run, for instance, in the central panel. And so just as a maybe as a follow-up study, what I'm suggesting here that might be interesting to explore potential tipping point across the last interglacial, so across this run, because maybe in the past the ice sheet was close to a tipping point, but then fortunately, just didn't pass this tipping point. And yeah, with this I would just conclude to leave some time for the question. Just to very shortly recap, we're looking at the existence of this SMB threshold for a complete melt of the Greenland ice sheet. We look at the processes controlling this threshold and the associated tipping point behavior of the ice sheet. And we do that with CESM simulations with different SMB levels from a fully coupled CESM simulation. And the key take-home messages that I think are important here, that we find a positive SMB threshold for complete ice sheet melt, and it's about 60% decrease from the pre-industrial CESM SMB, and we have a highly nonlinear response of the ice sheet, and this is basically determined by the competing effects of surface melt and GIA through the SMB height feedback, and we find this strong topographic control on the threshold. So the ice sheet is tipping when the central western margin is unpinning from a coastal region in the central west with high bedrock elevation. And yeah, that's it. Thank you. And I'm happy to take questions. And I'm really sorry for the missing videos.
Thank you, Michele. We have a minute for questions if there's any in the room. Yeah, Betty.
So great study. I'm going to have to go back and look at the slides again. One question, did any of the simulations, either the CESM or the CESM only, include changes in vegetation over these long time periods? Over Greenland?
Oh, no. Yeah, no, they don't. And that's, I would say, a major shortcoming, also thinking about the albedo. So no, we didn't apply any correction.
Well, it's still interesting. It'd be great to extend it to that in the future, but this has been a great study.
Thank you.
Any questions online? I'm not seeing any. Okay, Winter.
I have one. In your long simulation, it looks like the north of Greenland is kind of spared with the deglaciation. Is it because of the biases in CESM? Do you know?
Yeah, I think so. I think that's just because starting point is the pre-industrial, right? And then the SMB is increasing in the 4 times CO2 simulation. I guess, yes, it's basically just a remnant of the very cold pre-industrial SMB over the north in southern west.
Okay, let's just a couple of minutes behind. Let's move on to Miran. Is Miran online? There she is.
Yes, I am. Okay.
Yay! All right, can you share your screen, or would you like us to do your slides?
Share my screen, but I don't have permission.
Oh, you don't have slides?
I have permission.
Permission.
Yes, I need permission.
That's usually a issue with your own browser. You have to add the permissions inside your own computer. I think this is what Michele was having trouble with.
Can you make her co-chair? Does that help? Sometimes that helps.
Does it say it's because of the recording, or?
You've gotten really good at that.
Permissions in order to screen share.
Hang on. Where is she? Miran. Well, I can mute you and remove you from the call, and that's it. So.
And if I read you and ask at that point, shall I go and try again? Maybe it's faster, because at the beginning there's a question whether you want to present.
Just look at the slides. Some companions.
Yeah.
Should we go get somebody?
Yeah. Should we ever go ahead and email a presentation just in case?
Yeah, Miriam, could you email Gunter your presentation or link to it?
Okay. Yeah, I can do that.
Okay. And we'll,
This is Teresa.
we're having some issues.
Ah, okay. Shall I try?
Oh. So she said she doesn't have permission to present.
To present. Okay.
Do you know
I mean,
what I need to do?
yeah, is she emailing? Did I hear she was emailing you?
Yeah, to Gunter, but
Okay. Let me go back.
okay.
This is why I was it.
That needs soon too.
Oh, Elizabeth thinks that you have permission.
I hope he can make these soon.
Okay. Give me a moment. Okay. I'm gonna try again. No, doesn't work. Okay. I'm gonna leave. Okay.
Well, stick around. Just get to have.
No, she was just a minute, I think.
Okay. I had this problem in the presentation 2 weeks ago where my computer was not. Oh, it said she's in companion mode. That might be her problem, actually.
I can present it. I'm in companion mode,
Okay.
but I have her presentation now.
Yes.
Got all sorts of people. Elizabeth, all my friends, all the people that know things. Policy. Kind of media person. Is it possible to get rid of the screen on the right and I'll make this all bigger?
Yeah, if I go. Can you?
Going to present.
Would you like me to present for you, Miriam?
Yeah, okay. Okay. I'm sorry. Okay.
All the people?
No, I don't know.
Shall I start?
Yeah. Why don't you go ahead?
Go ahead.
Yeah, I go ahead.
Yeah. Go ahead, Miriam.
Yeah, okay, thank you. Okay, so here we are going to look at the effect of reductions in emissions on future Greenland ice events.
Dang it, I just broke it.
Wait a second, Miriam, please. We lost you.
Yeah, I was trying to just turn it down a little bit. Okay, can you go back again? Oh no. There's only one button on this thing and I set it up.
So, right? You didn't hear. Okay. I was muted. Can we go back?
Go ahead.
Okay, so we are looking here at the effect of reducing emissions on the melt of Greenland. At present, Greenland is contributing with 0.7 millimeters per year to sea level rise. This contribution is accelerating. And when we look at the future with the projections available, these projections have been constructed with icing models, HORSE, with the output from climate models. So there is no coupling there, and this prevents the representation of the interactions between climate and ice sheet, and in particular the feedbacks as well. Okay, so here the question is, how much do we have to reduce emissions, to reduce future ice sheet and mass loss rate? And so there is a time component here. It is about rates. And my approach is going to be to focus on the processes that cause high melt or less high melt. Next. Okay, so the tool here is the coupled community ice system model and community ice sheet model. It is described in this paper from 2021. We have a coupling of the freshwater fluxes with the ocean, and the surface mass balance is calculated in CLM. Next. So we have a set of simulations. Do you see my mouse?
No.
No. I stayed away to have a pointer. Okay, so you have here several lines. So the first one corresponds to 2 times CO2, so 1% increase to 2 times CO2. The brown is 2.5, the pink is 3 times, and the last two, the highest, correspond to 4 times CO2. And the line that you are seeing is about global mean temperature. And you also see a gray line, and this is a recovery, or let's see, like minus 5% decrease of CO2 to pre-industrial. Next. Okay, so I want to show you here projection up to 2100. This is the scenario SSP5 8.5, and we lose there 109 millimeters of sea level equivalent, and the CO2 concentration by 2100 is 4 times CO2. So I'm going to start by that. So what if we fix CO2 at 4 times? Next. So can you click on the video? On the, yeah, there. Okay. So this is a simulation of the evolution of the surface mass balance. So you can see how the red part is expanding towards a higher elevation. So the equilibrium line altitude is increasing in the simulation. The ablation area is expanding, which are the very same things. And then if you look at the time series, you have a red line that is for global mean temperature. By the end of the simulation, we have 10 degrees of global warming. There is Arctic amplification in here, and this is the blue line. So by the end of the simulation, we have 17 degrees warmer Arctic, and for Greenland, it is 19 degrees. Okay, so we are losing the ice sheet. So here, in these runs, we do lose ice in the north, and when the ice sheet is retreating, we enable tundra to replace the ice sheet, but not forest, so no trees. Next. Okay, so here you have a snapshot of year 500, and you have time series. So if you look at the black line, this is the sea level contribution in gigatons per year. 360 gigatons are 1 millimeter of sea level rise. So we have maximum contribution to sea level by approximately year 500. And then this goes down because the volume of the ice sheet is less. Okay, the ice sheet is lost in less than 1700 years. Next. Okay, so Here, if you look at the black line, you can see the evolution of the mean topography of the ice sheet. And when I say ice sheet, I mean the dynamical ice sheet that is losing area as well, okay? And you can see that at the beginning, the mean surface elevation is going slightly up, and also the mean ice thickness, which is the blue line. And this is because the first that we are losing are the areas at the margin that have the first grid cells to disappear are those that have less thickness. And therefore, when we lose that margins, then the mean ice thickness increases. Okay, but then later on, what we are seeing is a decrease in the ice thickness. And we have a green line here that is the bedrock elevation without considering isostasy. And what you can see is that at the end of the simulation, when the ice sheet becomes an ice cap, then it is retreating to a relatively high elevation bedrock area. And that influences a little bit what we are going to see in the following. Okay, next. Okay, so here we are looking at the evolution of precipitation. So the precipitation is increasing in time over the ice sheet. And we're going to separate that in three contributions. So the red and the orange lines are about global climate change, so what is, and elevation change. So both of them are contributing to increase the precipitation. So global change or global warming causes a wetter polar atmosphere with more precipitation happening over the area of Greenland and other polar regions. And the elevation reduction also is causing that the atmosphere on top of the ice sheet is warmer. So it's less dry because the surface is lower, so the atmospheric column is warmer. But also, at the same time, we have less of this orographic forcing at the margins that prevents the intrusion of precipitation towards the interior, so to call. At the same time, the change in the area moves the ice sheet away from the North Atlantic, which is the wettest margin of the ice sheet, and then this contributes to a reduction of precipitation. So here the precipitation is normalized over the ice sheet. Next, please. Okay, so here you can see the evolution of belt. These percents here indicate percent of area that is left. So the last figures are about the smaller 25% of the original area ice sheet. Okay, so we see how the melt is increasing, and also we see how the refreezing is increasing and also changing location. The refreezing is concentrated first around at the margins of the ice sheet, but as the melt is increasing, the elevation area is expanding as well, and we cannot refreeze when bare ice is exposed. So we lose refreezing capacity because we are losing a snow mass, and bare ice is exposed earlier in the melt season in many more places. Okay, so then the refreezing is concentrated more towards the interior where there is still a healthy sponge taking meltwater. Okay, we have a line there in panel B that again is about a partition. So what we can see is that approximately at year 750, when we are at half the initial size, the contribution of elevation change and global climate change to melt are equal. And then from the rest of the simulation, the main contribution to the melt comes from the elevation feedback. Yes. Please, next. Okay. If we think in terms of which energy fluxes at the surface are contributing to melt or to melt energy, we need to look first to what is coming. So the radiation that is coming in. And so the blue line is the shortwave radiation, and this is going down for the reason that with global warming, the model projects a more cloudy Arctic. So the shortwave incoming goes down. But the bad news is that this cannot catch up with the albedo decrease, and so then the net solar radiation is going to be very high, regardless of this reduction. And the long wave is increasing, of course, because of the global warming, more water vapor, because we have a warmer atmosphere here. Next. Okay, so here you can see how the ablation area is expanding. This is the percent of the total area, and by year 200, we already have 50% ablation area over Greenland. This has very important implications for the albedo. The albedo is going to drop a lot because we have earlier exposure of the ice in many locations over the ice in more and more locations as the equilibrium line altitude is going up. Please, next. Okay, so this is going to be reflected in here. So the black line is the evolution of the melt energy. You can see melt energies in watts per square meter. So here we are scaling by the size of the ice sheet. Okay, so this is continuously increasing, no? While the sea level contribution cannot increase continuously because the ice sheet is becoming smaller. No? We saw a maximum at year 500. Here there is no maximum. It is continuously increasing. Okay, so the main contributor to the melt is the blue line, and the blue line is the solar. So we have a main contribution here of the albedo feedback to the melt. Next. Okay. We have performed a 4 times CO2 simulation with one-way coupling. By comparing the two-way and one-way coupling, we can look at the feedbacks. And Tirsa Fenstra, who is presenting after me, will show you results about that, and also the results of a simulation where we go down with CO2 by 5% per year. Next. Okay, but now I am going to go with the reduction of emissions. So there is in this 4 times CO2, there is a very strong acceleration of the contribution to sea level rise at year 120. And we have seen how the ablation area is expanding, and by year 200, it's 50% of the area. So the question is, if we cap CO2 before this year 120 of the acceleration, what is the effect? So we are going to cap at year 111, and this corresponds to 3 times CO2. Next. Okay, so left is 3 times CO2, and right is 4 times CO2. And if we look to year 500, we see that the sea level rise rate, or the melt rate, is reduced to 1/3. Okay. Next. Next, and what if we cap at 2 times CO2? So this will be year 70. But now the picture is very different here. So I'm comparing 2 times and 4 times CO2 here when I'm looking at global warming. And so if we look at the blue lines, what we see in this simulation is that in the first centuries, we don't have Arctic amplification of global warming. So the Arctic warming is less than the global mean. And for the Greenland ice sheet, the annual mean temperature even is less than pre-industrial in over a period of several decades in the first 4 centuries. Okay, so what is going on? So you have to look at the ocean circulation. So this is the NAMOC index, and what is happening is that both in 4 times CO2 and in 2 times CO2, the NAMOC is weakening very much. And kind of similarly, but when you put the weakening of the 4 times CO2 global warming, it's not very obvious, the effect. But when we have a more moderate global warming, then the effect of a collapsed NAMOC over Greenland and the area of Greenland is very different because you have all this reduction of heat exports from the tropics, and this reduced income of energy makes a lot of an effect. And this is what we are seeing when we look at the warming. However, if now you look to year 400 for the NAMOC, you can see that in 2 times CO2, it starts to recover. So it recovers, and this has an effect in the plots about warming, and we are going to see the effect also over the ice sheet. Next. Okay, so
we're running
yes?
a little behind, so if you could start to wrap up, that'd be really nice.
Oh, okay. Okay, so the melt is increasing when the NAMOC recovers. Next. Next. Yeah, so this is ablation area expansion. So if you look at the blue line, you see that it never reaches 4 times CO2, but the ablation area expands a lot when the NAMOC recovers. Next. Okay, wrapping up. Okay, while we are seeing that the global warming goes more or less linearly with the CO2 levels that we are considering, this is not the same for the melt of the ice sheet. And we see a tight coupling between the NAMOC and the Greenland melt in some of the simulations. We have seen that there are important effects of albedo and elevation feedbacks on melt. And yeah, these are the conclusions. Okay, I'm going to leave it here then.
Thank you. Okay, so if we have maybe one question in the room. Okay, or you can take a quick check online. Okay, I don't see anything there. So thank you. Thank you, Maren. We can move on to Teresa on the role of feedbacks in climate mitigation. Teresa, are you online?
Yes.
Great. Can you share your screen, or?
We'll try.
Yeah, let's find out.
Have your presentation otherwise.
Yeah, I emailed you the presentation. Is she able to share?
We'll find out in a minute.
Okay.
Does this work?
Yay! Well done.
Great. Okay. Well, my name is Teresa, and I just graduated from my master's at the TU Delft. And today I will present some of the results of my master thesis, which I did together with Miren and Bert Wouters.
Could you enter
so,
code, please?
Well, we all know that the Greenland ice sheet has been contributing to sea level rise, and that this is increasing and is also expected to increase under global warming. But a Greenland ice sheet that changes...
Can you hear us? Real quick, are you presenting or are you just Because all we see is we don't see the slides in present mode.
Okay, then I'll try again. Do you see anything?
Well, we can see your slides, but they're not in presenter mode. Maybe it's doing the screen wrong. It's fine. We can see your slides.
So I just show the PowerPoint then,
Yeah, you're
not
good.
in center mode. Okay. Does this work?
Yeah, that's fine.
Okay, then I'll do it like this.
Okay.
Okay. So when the Greenland ice sheet changes and its elevation changes, this can also affect the local climate. But as Marianne already said, in most of the current sea level projections, we do not account for this because ice sheet models are just forced with a climate model output, and there's no two-way coupling between the ice sheet and climate. And besides that, the interactions between the climate and the Greenland ice sheet might also influence the response of the ice sheet when we have climate mitigation. So that led me to two questions, which I looked into during my thesis. The first one is, what's the effect of accounting for these interactions by doing a two-way coupled simulation, and how does this affect the Greenland ice sheet climate and the projected sea level rise? And the second one is, what's the role of these interactions in a scenario in which we reduce the CO2? So I used CESM2 coupled with the CISM2, and then we have two-way coupling between our ice sheet model, atmosphere model, and land model, and one-way coupling with the ocean model. The surface mass balance is computed in the land model and is downscaled to the ice sheet model by using elevation classes. And to investigate the effect of this, I also compared with a one-way coupled simulation. So in this simulation, we have fixed topography in our atmosphere and land model, and also fixed freshwater fluxes to the ocean. And for the downscaling to the ice sheet model, we then use a lapse rate of 6 Kelvin per kilometer. And I looked into this for a 4 times CO2 scenario, so 1% increase until we reach 4 times pre-industrial CO2. And then I compared the one-way and two-way coupled simulation to find the different feedbacks and interactions between the ice sheet and the climate. So first, I want to look at the mass balance and therefore the contribution to sea level rise. And we find that in our one-way coupled simulation, so in the simulation in which we do not account for all the interactions, that there are 17% larger sea level rise. And if we look at all the different components of our mass balance, we see that this difference can be found in the surface mass balance. Well, why is that? Well, I have two hypotheses. One is the representation of the melt elevation feedback. If we do two-way coupling, we can directly account for the melt elevation feedback, as our other model components know what the topography of the ice sheet is. But in the one-way coupled configuration, we parameterize the melt elevation feedback with fixed lapse rate. And besides that, some feedbacks that occur between the Greenland ice sheet and the climate are not represented when we do only one-way coupling. So first, I want to look at this melt elevation feedback. So in the one-way coupled simulation, we used -6 Kelvin per kilometer to downscale from CLM to CISM. But if we compute the lapse rates from our two-way coupled simulation, we see a lot of seasonality. We see very small lapse rates in summer, which might have a large effect on the computed melt. We see that these small lapse rates occur because our surface in summer in the ablation zone reaches melting point, and therefore a lot of the energy goes into melting the surface instead of heating the atmosphere. So we hypothesize that there is an overestimation of the melt elevation feedback in a one-way coupled simulation because we have a too large temperature lapse rate. Then I want to move on to some feedbacks and interactions that are not represented in the one-way coupled configuration. First, I want to look at the shortwave radiation. And what we see is if we compare our one-way simulation, it's the blue lines, with the two-way simulation, the red lines, is that there's increased reflection of shortwave radiation in our in both simulations, but more in our two-way simulation. And the reason for that is that we have a lowering topography and therefore a larger atmospheric column, but also larger temperatures. And that results in a larger amount of water vapor in the column, which causes more reflection of shortwave radiation, but also causes thicker clouds, which also results in more reflection. And therefore, this can act as a negative feedback on melt. And this increase in water in the atmosphere also results in more precipitation. So here I compared in year 500, which is the last year of my simulation, and I subtracted the one-way precipitation from the two-way precipitation. And we see an increase in precipitation, which is larger in the two-way simulation, and also that there's an effect of the ice sheet that moves more land inward because orographic precipitation moves more inward, leaving us with some smaller values around the margins. If we look at the contributions of snowfall and rainfall, we see that snowfall increases in the interior of the ice sheet as precipitation in general moves more land inwards, but also there's more water in this atmosphere. And this acts as a negative feedback because it increases our surface mass balance. But we also see a very large increase in rainfall because of larger temperatures over the ice sheet. And this can modify our albedo, which can then act as a positive feedback. And then I looked into atmospheric blocking. And over the last decades, there has been increases in summer blocking, and this is linked to increased melt over the Greenland ice sheet. But in our simulation, there's quite a large topographic change with a lowering ice sheet. And we see that if we follow this red line of the Greenland blocking index, that our blocking index decreases a lot. And this does not happen in the one-way simulation. So here we see an effect of the change in size of the Greenland ice sheet. And therefore, there's less blocking of the in the atmosphere. And we can link this to around 49% of the differences we find in the surface mass balance. And therefore, this decrease in blocking can also act as a negative feedback on melt. So to wrap up this part, what's the effect of using two-way coupling? We find that lapse rate of 6 Kelvin per kilometer does not represent our melt elevation feedback very well because there's a large seasonality that we cannot account for if we use a constant lapse rate. We find that there is a negative feedback coming from an increase of water in the atmosphere and an increase of clouds. There are changes in precipitation that can act as a negative feedback if this is snow, or a positive feedback if this is rain. We find a decrease in summer atmospheric blocking, which is a negative feedback. So we can conclude that if we do not account for these feedbacks, or if we parameterize them, we can have an overestimation of melt, which in our case was 17%, which shows the importance of also considering two-way coupling for sea level rise projections. And then I want to move on to my second question and look at the Greenland ice sheet response to a CO2 reduction scenario. And for this simulation, we, in the first 350 years, do similar 4 times CO2 simulation, but then after year 350, reduce CO2 with 5% per year until we are back at pre-industrial CO2. And we do this in a two-way coupled configuration to also see what the effect is of different climate ice sheet interactions. So if we start with the global response to this, a red line is 4 times CO2, and the green line is the reduction scenario. And we see that there's a very rapid response in annual mean temperatures over the whole globe. But that at the end of our simulation, which is in year 925, we still have a remaining 2 degrees of global warming. But if we look at the Greenland ice sheet, the response is a lot more complex. And we see that just like global temperatures, the Greenland ice sheet also responds very fast to CO2 reduction. And there's a rapid lowering of the temperatures over the ice sheet. But then after a few decades of a very low temperature, we see an increase in temperature. And to understand this, we have to look at the ocean circulation again. So here we look again at the NAMOC index. And like Mirel already showed, the NAMOC collapses when we have this high CO2 forcing. But when we reduce CO2 again, you can see that our green line shows recovery, and it even overshoots. However, this is a bit delayed compared to the atmospheric response, and therefore we first have this period of cooling, and after that period of warming. And let's see what that means for the mass loss of the Greenland ice sheet. So if we reduce our CO2 to pre-industrial, we can see that the mass loss from the Greenland ice sheet is halted quite rapidly, even though we still have this 2 degrees of remaining global warming. So we have to look at the surface mass balance and the mass balance to see why that happens. And what we see is that the surface mass balance, the blue line, does not recover to its initial values, but the mass balance does. And that's because the ice sheet has already lost 1.2 meters of sea level equivalent, and therefore the margins of the ice sheet have retreated, and therefore we have a lot less ice discharge. And this reduction in ice discharge can compensate for the fact that the surface mass balance does not recover. And this leaves us with a total mass balance that is around 0. And I want to zoom in a bit to this surface mass balance that doesn't recover. I want to look at 2 different components. The first one is refreezing. And what we see is that when we reduce CO2, our refreezing does not peak at the same level as it did during the CO2 forcing, even though there's a similar amount of meltwater available to refreeze. And we found that that is because we have a thinner snowpack. Our snowpack does not grow back to what it was before. And also that we have higher snow temperatures that are probably related to this remaining warming. And then we have the albedo. And here I plotted the albedo as a function of the distance from the margin. And the anomalies with respect to the pre-industrial values. And we see that the albedo increases a lot in the ablation area, which is below the black line. But in this area, it also does not recover if we reduce CO2. And this is the largest contributor to the energy balance that does not recover because less short-wave radiation is reflected. And so my final conclusions about this. We have ocean interactions that play an important role during the transition phase towards a colder climate if we can reduce CO2. We see a surface mass balance that doesn't completely recover, which is partially because of reduced refreezing and an albedo that does not go back to its initial state. But we also have reduced discharge because of a retreated ice sheet, which can compensate for this lower surface mass balance. And therefore, we can halt sea level rise despite this 2-degree remaining warming. And with that, I'd like to conclude, and I'm happy to take any questions.
Okay, that was nice to catch us up just a little bit, but I'm still going to take just maybe one question in the room. Go, Tree.
This is about the timing of the CO2 reduction. So there's obviously a point at which the snowpack was such that recovery in some sense wasn't possible. If CO2 reduction happened earlier, is there a chance to basically beat that tipping point?
Yeah, so it definitely depends on the timing of this reduction,
Yeah.
but I think if we already reach this 4 times CO2, we are already like too far in. So then the snowpack does not recover, and we have a lot of bare ice already. So then I think reduction should be like way earlier, even before we reach this 4 times. But I haven't looked into what exactly the timing of something like that would be.
I was just curious about your intuitions, whether there was a way to pinpoint what that point of stopping CO2 emissions was, such that there was a shift in the snowpack. It's really interesting work. Thank you.
Kelly, do you want to ask your question?
Oh yeah, thank you. Really amazing work. Amazing. I have a question about the second part for the recovery, and
Yes.
if you see any like a spatial pattern when there is basically the CO2 decrease. So if maybe some like the eastern that is more affected by the precipitation, and the EMOC is probably important for that. If you see some regional difference in the response.
I don't think I really saw a lot of regional changes. I think yes, what I mainly saw is that we have an ice sheet that retreats on like all sides, and therefore has less contact with the ocean. That was very important. But I haven't really seen regions that were more or less affected, I think.
Okay, thank you. And congrats again. That was impressive.
Thank you.
Thank you, Terza. Is Ziki Yan online? Oh,
Yeah.
he's right here. All right, cool. Sorry, I'm getting into the groove here. Do you want to try to share your screen?
What's the next presenter? Remote or?
He's right there.
Oh, nice. Oh, all right. But I do have a.
Still my.
Okay.
You got it?
Ladies.
Oh, that's good.
You might have shared the wrong window.
Yeah, you just need to bring up your talk. Instead of sharing the whole desktop, you might just share the window.
Yeah.
That's great.
My name is Ziki Yin. I'm from CU Boulder, and today I'm going to talk about this identifying energy balance drivers and feedbacks of Greenland ice sheet surface melt using causal inference. And this is an ongoing work as my second PhD project. So any kinds of feedback and suggestions is very welcomed. So we know that there are complex interactions between the ice sheet surface and the atmosphere, and resulted in several feedbacks that has already been mentioned by previous speakers. And surface melt results is impacted by these interactions and feedbacks, and is calculated. The melt energy is calculated by the sum of these 5 surface energy balance components. And as a main contributor to the ice sheet mass loss during the past decades, the surface melting has increased significantly. And on the left figure shows so the solid line, and this right square shows the hint cast by RECMO forced by Arrow 5 data, I think, and this dashed right line shows a simulation also by RECMO, but forced with CESM2, the highest warming scenario. And by the end of the century, it's projected that there's another 5-fold increase of the surface melt from Greenland ice sheet. And on the right is the daily Greenland surface melt extent from SIDC during the past 5 years, and also 20 and 12. And we can see this large intra-annual and seasonal variations. So we are curious about what drives these changes and the variation of the Greenland ice sheet surface melt. And this is a causal question. And causation is different to correlation that is commonly used in climate science. So this famous example of sunburn and ice cream consumption makes this clear, because during summer, the ice cream consumption and sunburns are highly correlated, but there's not a causal association, because it is the sign during summer months that cause both of these variables to increase. So the correlation can tell us the association between 2 variables, but causal inference can go further by identifying the direction of these links, and also account for this confounding factor like the sun in this case. And so we try to use causal inference to identify the causes for Greenland ice sheet surface melt variability. And by definition, causal inference is a method to formalize the pursuit of identifying, modeling, and quantifying causal relationships. And ideally, it can identify the physical mechanism from the complex interactions and make better physical understanding of the system. And there are 2 steps for causal inference methods. So first is causal discovery, which is to learn qualitatively the causal relationship among several variables. And the second step is based on this qualitative causal network to quantify the causal effects. So we try to use causal inference to answer these 2 questions. So what's the relative importance of these surface energy balance components and precises for Greenland summer surface melt, mainly on the like seasonal to interannual time scale? And also, under global warming, will there be a regime shift of this relative importance? Here are the methods we use for here. So for causal discovery, we are using this PCMCI method developed by Rangay et al. 2019. This method is suitable for time series with high dimensionality and nonlinear dependencies. So it's like suitable for climate variables. And here's a case of using this method to actually is a PCMCI plus. It's an extended version that can also detect both lagged and contemporaneous causal links. And this example shows it identified the causal relationship between climate variability, such as Pacific decadal variability and Atlantic multi-decadal variability. And we can see that the direction of the causal links and also the sign and the lag are shown in this causal graph. We are also using this extended version PCMCI plus for our case. And for causal effect estimation, we are using this path method. To use these two methods, several assumptions has to be made. So the first two are required by the causal inference method. So for causal sufficiency, it means there's no unobserved variables, and we achieve stationary through preprocessing of our data, and also because we choose I will show later, we choose a short time period, so we can assume linear dependencies. And the data we use also from coupled CSM2, CISM simulations. In this simulation, we also use this variable resolution grid, which has a quarter-degree regional refinement over the Arctic region for the atmosphere and land component. And this first run this 180 years pre-industrial simulation until the asteroid achieve near equilibrium state. And then we run this one-time CO2 increasing idealized warming scenario until it reaches 4 times CO2 and continue for another 210 years. And this simulation output monthly. The figure in the middle shows this time series of SNB and also SEB anomalies. And for the variable input into the method, as a first step, we only select so surface melt, and this for major SEB components. So the ground heat fluxes is not included here because of its relatively small magnitude. And for the time period, we select 2 time periods. So one is the last 50 years of the pre-industrial run, and the other one is the last 50 years of the warming scenario, so blue shaded in the figure. And for each variable, it is average over the ablation zone for during these 50 years, 2 time periods. And this colored grid boxes shows the ablation zone for these 2 time periods. And for data preprocessing, it contains 3 steps. So first is we use a decadal Gaussian kernel to remove the long-term trends. And then by normalization, we remove the seasonal mean and divide it by seasonal standard deviation. And masking means that the samples at the current time step can only come from the 3 summer months. But for the other time steps, like T-1, -2, they can come from other months. And this is the raw data, and then these are the after data preprocessing. And this slide shows the result from causal discovery, and these 2 lines represents the pre-industrial and this 4 times CO2 period. And if we focus on one of the causal graph, the color of the node represents the autocorrelation of each variable. and the color of the link represent partial correlation. And the numbers on the link represent the lag of the causal effect. If there's no number on the link, it means the causal effect is contemporaneous. So it happens within the monthly time interval. And because we also use a bootstrap method here, so the bytes of each link represent the detection rate from 200 realizations of the sample. So the wider the link, the more robust it is. And I also include two significance level here. So one is 0.025 and 0.05. So the lower this level, so basically less links will be detected. And then if we compare, if we look at this for causal graphs, we can see both net short wave, net long wave, and sensible heat fluxes have a positive link towards melt. And also for this warming period, we also detect this positive causal link from latent heat fluxes towards melt, which means that in a warming scenario, this latent heat become more important for surface melting. And also we did, for all of these cases, we detect this positive melt albedo feedback between net shortwave radiation and melt, and the melt's impact on net shortwave radiation is 1 month lag. And also for the pre-industrial condition, we also found this negative feedback between sensible heat fluxes and melt. And for these links, our focus here is mainly on the causal links related to melt. So for the other links between the surface energy balance terms, because we assume in this method we assume there's no unobserved variable. So these links maybe not physical because, for example, for the link between long wave and short wave, there could be a confounding factor like cloud impact on both of them. So it's not a focus here. And based on one of these, so based on the left two causal graph, we estimated the causal effect here. So for the links with, for the contemporaneous links from short wave, long wave, and sensible heat fluxes to melt, we found that, so the pi control simulation is showing in blue here, and the red dots here shows the warming scenario and with 90% confidence level. So we detected that the importance of these radiative fluxes become less important with the increasing importance of these sensible heat fluxes. But both of these two time periods, the net shortwave radiation remains as the dominant contributor to surface melting. And also I want to note here, this is only the quantification of this direct causal effect. So directly from short wave or long wave towards melt, it doesn't include indirect causal link, for example, from long wave towards short wave and then melt. And to estimate the total causal effect, a more complete and more robust causal graph is required. And currently there's a problem in our causal graph that sometimes these causal links are not very robust. For example, here in the right corner, the links between long wave radiation and melt is misdirected in this case. And to work towards a complete causal graph, I try to include some other variables that related to the causal relationship here. So for this two causal graph in the boxes is a previous result. And first I tried to add cloud fraction here. And we found some meaningful causal links that positive effect from cloud fraction towards net long wave radiation, and also a negative effect to net short wave during the warming scenario. And then I also tried the blocking index and the two near surface temperature. And also we found this link between GBI and the near surface temperature, and also sometimes the surface temperature cause a positive effect on sensible heat fluxes. But the problem also, so we also have problem here with some of the links is misdirected, and also we lose the link between from net short wave towards melt in these two cases. And this last column includes all of these three new variables, and it has a similar problem as the previous one. And another way I tried is to use another extension of this PCMI method, which allows observed variables. So here for this method, I use the same 5 variables. And if we look at this link between net long wave and net short wave, there's a double head arrow. That means there's a confounding factor that is not included here that caused this relationship, this causal link between these two variables. But again, like in the warming scenario, this the link is different, and so it's not very robust. But for this method, there's a way to implement physical knowledge into this causal graph. Like you can define a causal link based on the physical knowledge, and that's one thing I want to try later. So to summarize, this causal inference method can let us focus on fewer important drivers, and it can detect the lagged feedback loop for Greenland surface melt. And for both the pre-industrial and the warming scenario, net short wave radiation acts as the dominant direct melt driver. But we detect this increasing role of turbulent heat fluxes for the surface melt. And we can see it's challenging to establish this causal relationship for a complex system like the climate variables. And so robust design and also trying multiple methods is necessary. And there are some steps I think I can continue later, like experiments with more variables and model parameters. And so in the end, I want to summarize this a robust causal graph, and based on which I can estimate the total causal effect from different factors towards melt. And also there's a way to implement physical knowledge. And also there's another student from the University of Maryland. She's using like similar causal inference method, but she's using observations and reanalysis data. So I think it will be helpful to compare the results from our case based on CSM study and from observations. Yeah.
Okay.
Thank you.
Yeah, it's great. Thank you very much. Okay, we are running a bit behind. Maybe we'll ask for questions to be held until the break. Is that okay? And thank you very much. So our final presenter before the break is John Moore. Is he online or in the room?
In the room. He's in Finland.
He's in Finland. Okay, John, are you online?
Can you hear me?
Yes. Great. Oh, that's great.
You see my screen? Okay.
Yes.
Yeah, thanks very much for this. Shall I start?
Yeah, oh, please go ahead. Thank you.
Okay, yeah. Yes, certainly. Thanks very much. And basically what we're trying to see here is exploring the limits of what might be possible as a kind of an intervention for the ice sheets by comparing Jakobshavn and Thwaites glaciers. And of course, this is a joint effort with a lot of different people. So what this slide here shows is two guys covering with a blanket a glacier in the Swiss Alps. Of course, this is very different from any kind of ice sheet intervention. But the point is, it illustrates that these two guys are not imagining that this blanket is going to solve the climate crisis. And equally, the guys at COP28 or whatever are not going to call them up and say, hey guys, we've got this covered, don't worry about it. The point is, everybody knows and accepts that it's the CO2 mitigation that is the ultimate goal, and we have to draw those concentrations down. That's 100% clear. But in the short term, we also might need to take some active conservation roles to deal with very vulnerable elements that are simply reacting too fast. And there is, of course, evidence that there is this kind of tipping point behavior, and we are approaching the point whereby especially the ice sheets are unavoidably going to be melting away, particularly the parts that are vulnerable to the marine ice sheet instability. And of course, we're not here looking at dealing with situations over the whole ice sheets. Essentially, we're just looking at these marine ice sheet instability vulnerable outlets in Greenland and Antarctica that are circled here. So we're lucky that the non-Newtonian viscosity of ice focuses the flow into these kinds of narrow outlets. So in a sense, you get a lot of leverage that you don't need to deal with the whole coastline or the whole area of the ice sheets if, in a sense, we can put the plug back into the system. So this illustrates the rough idea of what we call seabed curtains. So you're probably familiar with these plastic curtains that separate fluids of different temperature, in this case, cold air inside a freezer room and warm air outside. But of course, the curtain can be pushed aside by people or vehicles going through. In the setting of an ice sheet, the idea is that you have something that limits the inflow of the saline and warm bottom waters towards the glacier. So you're trying to lower the thermal forcing that's acting on the glacier. And as I said, this fact that the main outlets are confined in relatively small width outlets gives you this large leverage. But anything that you do, you want to be able to remove it in case of some unexpected effects. So everything should be at least as easy to take away as it would be to put in the first place. And in this case, this is the advantage of having this kind of flexible curtain that does not provide any physical buttressing, but simply blocks the inflow of the water. So it's relatively easy from an engineering point of view to remove these. So we looked at where we might put those kinds of blocking barriers in. And this map shows with the pink arrows how the warm water flows in towards Thwaites and Pine Island Glacier through deeper channels incised in the seabed. And in fact, the water flows through the Pine Island trough from the a continental shelf margin and then separates into finer troughs. So the particular thing that we're talking about is mainly the OB, the outer bay curtain route here. And if we look at the bathymetry, we can see that the channels closer to the glaciers are incised in deep bedrock troughs, and the outer bay is in a sedimentary regime, and so the channel is much shallower, although of course it's much wider. It's interesting that the route in towards the Western Thwaites is only 4.5 kilometers across, and of course this is the most vulnerable ice sheet on the planet. In a sense, if you block that one, it would be very effective. But on the other hand, the water may flow through some of these alternative routes instead. Whereas if you block something that's in this main inflow, you could avoid that kind of easy hydraulic connection closer to the glaciers. So this is a simulation with a 10-kilometer resolution model running for 10 years. And this includes on the left a curtain across the Pine Island trough, and on the right the control simulation, and the colors represent the temperatures at 550 meters depth. So if I run the simulation, you can easily see that the temperatures inside this curtain are about 1 degree cooler than the temperatures elsewhere, and the rest of the domain doesn't have significant differences in the temperature. And of course, this is because the warm water isn't really diverted anywhere else. It just raises the height of the thermocline by about 1 centimeter by excluding this area, this volume of water from the global ocean. If we take a cross section through the trough, so here we've got the continental shelf, we've got salinity, and we've got temperatures, and with the curtain and without the curtain on the right, you can see that it blocks this temperatures, and that in the parameterization that Nakayama uses produces a lower melt rate at Thwaites and Pine Island. This is just a parameterization, but then that can be plugged into Matthew Morligem's ISSM model, and looking at the grounding line of Thwaites without a curtain and with a curtain, and there is few lower retreat rates in Thwaites with this curtain compared with without. This is just the first simulation, and there's lots of potential differences that you might make it by changing that parameterization. But no one would go to Thwaites as the start. You would try to build up any kind of interventions gradually through smaller scales and learning and trying to, of course, find off-ramps if anything proved to be infeasible, or social license was not granted, or policies and financing didn't happen. So we've been working quite a lot in Greenland, in Ilulissat. We did also surveys there, but we have a model, and this is the bedrock topography there with the deep trough, and we wanted to see what would happen with the bicycles model of the ice driven by the different interventions. And of course, the difference with Greenland is the surface forcing is very significant, as well as the ocean. And we can see in the future under SSP 585 a lot more runoff, which goes into the subglacial outflow compared with SSP 245. Additionally, we find the ocean, the seasonality. This is the 4 seasons, and going from the historical into the future. We can see that in the summer and autumn periods, there is none of this stratigraphy, depth stratified layering, where you have the warm water below the cold water. It in fact is the opposite way around. And in fact, what we find when we look at different barriers at the mouth of the fjord, that it makes almost no difference to the retreat. This is the profile along the center line of Jakobshaven. And you can see with no barrier, you get retreat of the grounding line, and you can put a 50-meter high or 100-meter high barrier. And it makes small differences, but very small. But there are differences between 245 and 585 in the retreats that are observed. But again, curtains don't seem to make much difference. And even when you change the ocean temperatures and the atmospheric temperatures back to what they were in the 1990s, you still get a retreat occurring. So essentially, the intervention makes no sense. It makes no difference to what happens to the Jakobshaven glacier. We also looked at the attitudes of local people and see what they felt about any kind of an intervention. And it was very clear that because they were concerned about the possible impact on fishing, that they certainly did not want any intervention there. They are perfectly able to adapt, as they have done, to changing fish species or the position of the terminus in the glacier. On the other hand, fishing is not so important in many other glaciers where there isn't a local community. And working with the Inuit Circumpolar Council and other officials in Greenland, they were quite eager for us to not forget the potential of the rest of Greenland, because every inch of sea level rise averted is worth something like $1 billion per year throughout the 21st century. And the Greenlanders see this as a potential source of income that would be rewarding their stewardship of the ice sheet. But obviously, this is all very much in the future. So yeah, that's where I'm finishing. I have no idea what the time went like. Okay.
That was great. Thanks. Thank you. Yeah, that worked out perfect. Thank you, John. So we have a few minutes to discuss these geoengineering options and efforts, and then a break is scheduled for about 10:30.
I think I can take over here. Thank you, John. Can you stop sharing your screen, please?
Sure.
Oh, there you are in person. So let's see. Yes, it's in here. So I would like we would like to for everybody to now join into a discussion. So these ideas in geoengineering is what has been talked a lot about in the open for the Land Act Working Group is a little bit new. So this is a space that we haven't entered yet, and so now with this talk we have this is a topic that gives us the opportunity to talk about it. And so in this next 20 minutes, I would like everybody to share their thoughts, to share what they think about geoengineering in the Land Act Working Group, and in particular, we came up with two questions here. That's not the only two questions to be answered, but when it comes to this group here, what do people think? What governance mechanism should be in place to ensure ethical and responsible science that we can do within a global climate model or within an ice sheet model? And what are the science problems that we could investigate in the near term and longer term with more model development? So there's a lot of personal feelings about geoengineering. That sometimes, it could be scary. It could be, we all have our own. But there's also responsible science that can be done with it. I would like just to open the floor to whoever would like to start. And if you're online, please raise your hands or unmute yourself, and please hesitate to speak up. Yes, Betty.
So I'll start. So thanks for that presentation, John. That was very interesting and thought-provoking. One question you mentioned, like in Greenland, I forget where it was exactly, but the local populace didn't want this type of intervention because of the fisheries. But do we need to think a little bit more broadly, even around Antarctica, if we start doing this, how it affects marine mammals, fisheries in a broader scale, even if it's not a place where people are actually fishing? Could it change our ecosystem longer term, I guess?
Yes, I think that's an entirely valid point to make. The point about any intervention is that you do not want to have any losers. And it's, of course, socially unacceptable that the Inuit, for example, in Greenland should be expected to make some kind of sacrifices for the global good. No, there has to be benefits at all scales. It's important to think in terms of Antarctica about the risk scenario. So it's not so clear that you should be comparing a geoengineered future with the present, because the present is not something that we're likely to continue experiencing, especially if marine ice sheet kicks in. So you have to look at what will happen to the marine life, for example, if Thwaites Glacier, Pine Island start to collapse and you get a meter or two of fairly rapid sea level that we know have happened in the past. In terms of the direct impact of, for example, building a curtain like this, yes, it would be humanity's largest ever engineering project. But the marine biologists that we have spoken to are surprisingly sanguine about it. They say things like, well, fish can swim. You know, we're not blocking the entire inflow. It's on average, this curtain we've simulated, about 100 meters above the sea bed. So there's still 400 meters of open water that things can swim through. And also the curtain is probably going to be more like a net. So it isn't going to be entirely impermeable or non-porous. There will certainly be some openings or gaps naturally occurring in it. It's essentially going to be impossible to make a pure solid thing. And obviously, when it comes to maintenance, you want to be able to take sections in and take them away. So there has to be a tolerance of any intervention for imperfections within it. You know, if you've only got 90% of the curtain there, it's no use if it's zero effectiveness. If it's 90% there, you want it to have at least, say, 50% effectiveness.
Yeah.
Yep, yep. John, this is Bill here. I've read a little bit about this like in the newspaper article that came out in the Times recently, but I was wondering if you could say a bit more about the financing for this. The ballpark estimates you've come up with for how much it would cost to do something like this in the Thwaites region. And although it's speculative, who are the people that you've talked to who may be interested in funding different aspects of this, including the investigative phases and scientific research?
Yeah, well, of course, it has to be, you have to remember that we are very much at the research stage. So in a sense, what we have is an opportunity for the science of glaciology, for example, to, in a sense, become also an applied science, where people are looking for the kinds of simulations that people are doing as a way of maybe making a practical difference to sea level. So in a sense, it's about growing the research pie, attracting people in like philanthropy funders who want simply to make a difference to the quality of life, especially in the global south, which are very vulnerable. The actual cost of building a curtain in Thwaites would be, we estimate, something like $50 to $100 billion. Of course, that seems an enormous amount of money, but the damage expected throughout the 21st century for every meter of sea level rise is of the order of $50 billion per year. So if this kind of curtain removes that kind of high-end risk, say a meter of sea level rise, then it's pays for itself essentially within 1 year of the damage that would otherwise be caused by it. But we're not asking for 50 billion straight away, of course. This has to be built up, as I kind of showed with this ladder. You start off in tanks and inside experiments, always looking for red flags and reasons why it's infeasible. And then you move out outdoors to small fjords without ice involved, just to look at durability, engineering design, those kind of issues, while all the time working with lawyers and policymakers and governance in general to see everything has to be spun together. It's not just about the science and the technology.
And who coordinates this, and who supplies the seed money for the smaller experiments and the research you're talking about?
Well, a lot of it has been done by my group, but there are also people, for example, at MIT that are looking at approaches to trying to slow down the ice streams by increasing the basal friction, essentially drying the bed of the ice sheets. That's an alternative idea. I personally would like as many tools in the box as possible, and we just have to need people to simulate these things, because of course if you slow the glacier down but keep the thermal forcing the same or increasing over time even, then that grounding line will start to retreat, but the ice will have this huge thick floating part that hopefully would ground and provide the buttressing that we're looking for by lowering the melt rates as well. The kinds of people that have put this money into it are, for example, additional ventures who are funded or seed funded by one of the guys that started with Facebook. There are a Swedish billionaire who's from the pharmaceutical business, who's had a long history of supporting Arctic and Antarctic research. And so he's put some money into it. And now various other NGOs and philanthropies are very interested, but we're still at the very start, the very early stage of trying to decide where we would put the money. The idea being that, for example, the University of the Arctic, which is very good connections with the indigenous population in the Arctic, might act as re-granters. So they could take money from philanthropists and then give it to experts in the particular areas, the scientific areas, but also the local areas and people to understand what the impacts might be from an indigenous perspective.
Okay. One last question. Do the people in Europe who traditionally fund science, do they have any interest in funding this?
Well, state funders so far have been very wary about the optics of funding any kinds of geoengineering. The UK now has a new funding body called ARIA, whose remit is very high risk research. And these guys have just launched a $50 million program that will look specifically at climate and weather management options. And these guys certainly are. I think it's important to have a combination of private philanthropy money and state money. It really raises the credibility of the research. Philanthropies are only interested in bridging the gap between a kind of crazy idea that's difficult to get funded because of the state committees involved in national funding, and some people have a very, very strong emotional rejection attitude to anything like this. So philanthropists see themselves as providing a few years of this bridging funding until major national funding comes online.
Okay, thank you.
Kim, you had your hand raised earlier on.
Yeah, that's correct. Hi, John. Great talk, by the way. I've never actually I've read a few of your papers, but I've never seen them presented by a person before. So that's cool. I was reflecting a little bit on the first question on the slide right now, like what government mechanism should be in place to ensure ethical and responsible science. I really like your latter idea where you take it up from the tank and then take it up to the Svalbard glacier, then take it up to Jakobshaven, and then take it up to Thwaites. You could, and that's just a wild thought. You can apply something like that also in like model code or something that you say like before we publish anything, we're first going to publish it in a small scale, then we're going to do it at a bigger scale. So of course we can, like you do, we can probably construct a setup like this in the community action model and do some simulations with that. But we shouldn't maybe publish it because we don't know yet what our modeled small scale stuff will do to ground it a bit better. And a related question to that is actually like you showed that it for Jakobshaven didn't matter if you put curtains in the fjords, but it does matter for the Thwaites region at least a little bit. Like what is the why is that? Why do you think that that happens?
Well, I think fundamentally it's because the atmospheric forcing is so important in Greenland now. So in 2003, Jakobshaven lost its ice shelf, and you could imagine that the ocean has more leverage the longer the ice shelf is, and essentially what you want is to increase the buttressing. I mean, that's what's really slowing the glacier down. So if there's no prospect of an ice shelf forming at the moment in Jakobshaven, then it's the most unstoppable glacier on the planet. People like Alex Robel said when we had a meeting in Chicago, just because it's so out of balance with anything like the present climate. It's doing its marine ice sheet instability thing. Of course, the worry is that the same kind of thing could happen in Pine Island or Thwaites. Of course, the bedrock is different. You've got very rough topography there, so it's really difficult to know. I mean, when we had a meeting in Stanford with about 60 glaciologists and oceanographers, there was a full spectrum of some people saying, well, I don't think there's anything to worry about, Thwaites might be stable for 200 years, and other people saying it's too late to do anything, Thwaites is completely gone. So we don't know for sure, and clearly we need a lot more resources put into doing this kinds of simulations. So I'd a little bit disagree with you. I think it doesn't make sense to sort of start on this ladder unless we think it's going to have a big impact on something meaningful like global sea level. To really understand that, though, we need, for example, 100 times the number of unmanned underwater vehicles than we've got now. People have kind of one, and they were so worried about losing it. But if we have, for example, some tech bros at in the Silicon Valley area, really interested in understanding if we could get the cost of a UUV down from 2 million to say 20,000, we could have 100. And, the interesting regions could get very quickly a lot of data that we might improve our models with enormously like that. But further, yes, from the engineering point of view, you have to consult with the guys that really know how to build structures in deep water, and unfortunately or fortunately, these are exactly the people that have been responsible for the problem, in the sense that a lot of it is deep sea drilling for fossil fuels, but also for offshore wind turbines and communications cables and things like that. But these guys know how to do this kinds of fluid material interactions and understand the real engineering concerns about durability. You don't want to introduce, for example, plastics into this kind of sensitive environment. So the Norwegian company we've worked a lot with, called Aker Solutions, came up with this plan to make it completely biodegradable. So all the materials would be things like hemp and canvas and things that would essentially dissolve over time. So that's the kind of thing that specialists bring. We glaciologists cannot hope to look at everything, but there are lawyers and engineers and policy people that are very motivated, and essentially they've given up what they were doing because they understand a big problem. It's worth tackling. It's worth making a few personal sacrifices. I mean, the glaciologists doing this are kind of doing it in their coffee times and after their main projects are finished, just because it's a worthwhile project to pursue.
Thank you. Clear.
So with respect to the first question, and here this is a question to this entire community here present online in the room. If we were to try to engage in this type of science, would you feel comfortable with it? And what do you think we should put in place, within the limit of the Lindex working group to be responsible about this type of studies? How do people feel about it? Yes, Miriam?
So just a couple of quick ideas. So the first one is transparency about this. The second one is mechanisms of control. So there are people who are who see a risk of distraction with the primary with the primary control of climate impacts, which is reducing emissions. So for instance, I am part of a proposal on geoengineering by sulfate emissions into the stratosphere, and we have an external advisor of the project that is a skeptic of geoengineering, and because he's a scientist that is pushing very much towards reduction emissions, and it's very skeptical about the added value of the geoengineering. And this introduces a control mechanism because, all point of view are included, and so the pros and cons. I think what is critical is that in the governance is that the transparency about the pros and cons, and
To be a paradigm shift towards publishing negative results as well as positive ones. So if an intervention looks like it's going to fail, then it should be out there so people, first of all, don't waste a lot of time reinventing it later down the line, but also because, in a sense, it's important to be transparent. Yeah, things may not work. In terms of the funding, for example, there are existing codes, for example, that we have in University of the Arctic that says that we don't want to take money from people actively exploiting fossil fuels, for example, because they would see that as maybe greenwashing or something like that. But an organization that divested from fossil fuels 50 years ago or something, there's no big problem with that. It's the tip. Universities do this kind of thing quite often, and certainly in terms of governance, yeah, you absolutely want to have people that are disinterested in gaining, funding for students or something like that. We don't want it that I'm the guy that decides who gets the money. That's clear, for sure.
Would it make, yes, Betty?
Make one more comment, and I don't know enough about this. I was thinking about the sea level fingerprint right now, but we just have to be concerned, are there winners or losers by doing this? I know in some cases, like the geoengineering, where they're suggesting throwing up lots of aerosols into the stratosphere, besides just what it does to the atmosphere, there may be shifts in precipitation patterns. So there may be winners and losers. This seems like that would be less so, but I don't know enough about it.
Yeah, because of the self-gravitational effects, then the higher than average sea levels tend to be in the global south around the tropics. And of course, sea levels going down around Greenland. That's their problem with sea level, that they're getting holes in their fishing boats. But of course, most of the impacts will be in the global south, and yeah, much worse than, for example, in mid-latitude countries.
I just want to make one point, which was, I think that is this affecting the global south as opposed to can you convince that you're helping the global south? Like, is the argument one that all of the people affected can actually understand, even if you are improving their lives? So, I mean, the question I worry about, or that I think about with this is, even if you did improve people's prospects in the future, how could you prove that to them? I mean, what communication would it take? You know, what trustworthy resource would be required to convince somebody that they should believe that you improved their lives, saying that, oh, these are very smart modelers, we're all very smart people. I don't think that works anymore. And if it ever did, and it's definitely not going to, and you know, if we look around the room and who's actually modeling, who's making these decisions, why would someone who's affected trust us that we helped them?
I can tell you that I've just been refereeing a paper where they interviewed 30,000 indigenous people around the world, 1,000 people in 30 different countries. The most trusted source of information was universities, and
So that's not surprising at all.
Yeah, exactly. So what was surprising was that indigenous groups seemed better informed about geoengineering in general than the general population. And this might be because, of course, a lot of the people in the global south, and particularly in marginalized communities like indigenous groups can be, are directly impacted worse than the general population, certainly globally. So they are already feeling extreme floods and things like that. So they kind of get it.
I think there's a paper by Ken that actually made that point exactly, that there's, Ken had forwarded me this paper that's already published or whatever that was making that point, is that it's not clear that everybody in the global south or affected communities hate geoengineering. It may be that we're more suspicious because of cultural reasons than they are, which I think is interesting. Yeah. But I think, you know, but that's not quite the question that I was, you know, or the concern that I was pointing out, is that saying, hey, we might be interested in geoengineering, we might trust universities, that, you know, like none of the idea that, you know, these people would be distrustful of universities doesn't, you know, I wouldn't intuit that anyway. But the question is, there will be impacts. There will be extreme impacts. There will be, you know, sea level rise is probably going to happen no matter what. If you go up and you say, no, I assure you that we, you know, it's bad, but it could have been worse if we hadn't done this thing. And how would we prove it to them? And because, you know, you may trust universities, but if you're being impacted, being able to, I mean, we have a hard time, you know, settling attribution right now. How would we prove it to people when we've done something, when, you know, the world has done something really, you know, that's changed things, and we simply assure them that it wasn't because of us. Any case, so, you know, I take your point that, you know, you have these populations that they're open to things, but I do, you know, it's the after the fact saying that, you know, do you, we know the bad things are going to happen. We're not preventing everything. So how do you disentangle the drivers?
I think you're right that the messenger plays a very key role, and there are trusted messengers, at least in the Arctic, and I don't know about the global south, but I mean, I already mentioned the University of the Arctic. That is trusted within the indigenous population because it's sort of been largely by the Arctic for the Arctic. So yeah, but the messenger is as important as the message if you really want to change people's hearts about the attitudes.
Well, and I think that one of the things with Antarctica, what's interesting is you have the Antarctic Treaty, you have, you know, the signers there, most people, you know, as the sea level fingerprint they're pointing out, it's mostly affecting people in the global south who have mostly been screwed over by people who are on the Antarctic Treaty. So we've all decided amongst ourselves that this is a great idea, and someone who's actually in Bangladesh, is like, I'm not sure I really trust you given, I don't know, imperial history. And none of it, all of this is completely separated from whether it's successful, whether the science is successful or a really great idea. Okay, maybe, you know. Yeah, anyway, these are just thoughts.
The legitimacy of something like the Antarctic Treaty is a very valid question. You have 29, basically the rich nations that are deciding things that are an existential risk to countries like Kiribati. And how do they have a voice in this? The Antarctic Treaty has to, or the members have to adapt to remain relevant, because in a sense, the rest of the world tolerates this Antarctic Treaty system because it's not sufficiently objectionable to do anything else about it.
Well, sorry, I'm done.
Oh, yeah, sorry. It's a wonderful discussion to have. I'm very glad that people are passionate about it, but we like way into our breaks right now, and we want to make sure that we get a break before we continue on with the second part of our morning. So thank you so much to all the speakers this morning. Thank you, John, for this interesting discussion. And let's rejoin in 20 minutes, if that's okay with everybody. And Tim, before you go on the break, can you make sure that you can present your slides?
Yes, I will.
Listen to one of the oceanography
Hello again,
talks.
everybody.
So I'm not deserving.
Let's continue the second half of our meeting, and we're going to start with Tim. To be able to present because he tried and it worked.
Yes, we did. And now it's going to go smoothly in one try. Can you see the presentation?
Hooray.
Yes. Great. And if I do this?
Yes. Awesome.
Even better. All right. Well, then I'll start. So I'm Tim. For this project, I work together with Bill and Gunther, who were there in the room, and Willem-Jan and Roderick. Roderick tried to join, but apparently he failed, so he left from the Utrecht University. And I'll be talking to you about basal friction. So the first part of the meeting, about 10 minutes, I think, and the flow factor inversion that they recently tested with. It gives some very promising results. So it's going to be the last 5 minutes. It's not mentioned in my title of my on the abstract of the agenda. Apologies for that, but I just came up with it and I'm quite stoked about it, so I wanted to show you. So the first part about basal friction is basically about the West Antarctic ice sheet collapse. So as some of you know, we have done some simulations with the observed present-day mass change rates. We feed it to CESM, and CESM gives us a collapsing West Antarctic ice sheet, basically for all model settings that we tried. So what you can see to the right here in the graph is the West Antarctic ice sheet collapse in different flavors. So we took the community ice sheet model and we applied several different parameterizations. We applied different input data sets. We even tried a different ice sheet model. So we tried it with euphemism as well, the Utrecht model. And we found that for every setting that we chose, the West Antarctic ice sheet collapses. However, there is quite some differences in how sensitive this collapses to different model choices. For example, the basal melting, the purple lines, are wide apart. So the uncertainty related to the basal melting in CESM right now is quite large. The ice dynamics, however, the blue lines, are relatively grouped together. So they're kind of, the uncertainty related to that's kind of small. And actually, if you exclude the outlier, the slowest blue line, so to say, with the crosses, that's about the rheology of the ice, then you're left with basically the basal friction laws. And those are grouped around the black default run. So actually what I want you to take away from this picture is that if we simulate the West Antarctic ice sheet collapse in CESM, the uncertainty in this collapse, in the timing and in the speed of it, does not come from the basal friction. You can choose the power law, you can choose regularized Coulomb law, it doesn't really matter what you choose, your collapse will look the same. And that's what made me curious. I mean, there's a lot of people that wrote stuff about basal friction. Some of them, actually a lot of them, argue that basal friction is paramount in making correct sea level rise predictions. So you need to parameterize it in a rigorous and fitting way. what we find is basically you can choose whenever one law that's around the literature, and you will find the same thing. So I want to understand why that is. So what you see here is some characterizations of 3 basal friction laws that I use in the community ice sheet model. It's you could maybe focus a bit more to the graph on the left, which shows basal friction on the y-axis and basal velocities on the x-axis. And you can see that for 2 of those laws, the green and the blue line is Coulomb sliding, where as the basal velocities increase, your basal friction does not increase anymore. But for the power law, it does. So for the power law, there is an ever-increasing basal friction with basal velocities. This gives a kind of a stabilizing effect. Like if your ice sheet or if your outlet glacier starts to accelerate, your friction will increase, and therefore it will dampen the acceleration a little bit. This does not happen for the Coulomb sliding laws. So what I did is I did some regional case studies on the Amundsen Sea embayment and the Seipel coast, and basically to see what the effect of the buttressing was. Because as a first hypothesis, and this is still preliminary work, so there is no definite proof yet if I'm right or not, but this is what I'm investigating right now, is that if you apply this Coulomb-style friction that asymptotes for large basal velocities, that means that you allow larger ice velocities to happen. This ultimately means that you also allow a larger grounding line flux to happen. So more ice will be transported from the grounded part to the shelves. This initially will cause more sea level rise, but because, for example, in the Amundsen Sea region, the outlet of the glaciers is in a confined area with a lot of mountains and pinning points and places where the newly formed shelf can get stuck. Or at least I think that as soon as the grounding line flux increases, that also your shelf thickness increases because there is simply more ice advected to it. And this thicker shelf will buttress more, so it will stop the grounding line from moving, or at least it will prevent it from moving super fast. So that's why I also chose the Seipel coast region as a comparison study, where as soon as you remove parts or large parts of the Ross ice shelf, all the glaciers or most of the glaciers at the Seipel coast will become completely unbuttressed and can flow into the ocean completely freely. To do so, I had to raise the temperatures in the Seipel coast region or under the Ross shelf with 1 degree, which is quite a lot, but otherwise it wouldn't be comparable to the collapse that we observe in the Amundsen Sea region when we run the CESM. So after 500 years running forwards, and I'm just going to show you the Amundsen Sea region results because I'm simply just not finished with the Seipel coast region. I have the data, but I still need to take some time to think about it and make some plots. What you see right here is on the top, you see the grounding line after 500 years of running with the observed mass change rates. So you can see that there is a retreat ongoing. Red means that the ice has thickened with thinned with respect to the spin up. So the initialization, and the contour lines, so the blue to yellow contour lines, are ice surface velocities. So the first thing that you can see is that for the left is the regularized Coulomb law, by the way, and to the right you can see a power law, a classical one with ever increasing basal friction with basal velocities. You can see that actually for the power law, the grounding line recedes faster than the regularized Coulomb law, which seems counterintuitive because it allows less or lower velocities. However, also a thinner shelf. So the thinning will be largest around the grounding line over there. And actually, if you compare those 2 figures in terms of sea level rise, they are very comparable. So however, that the grounding line is not the same position, the sea level rise that came from this 500 years of running with either one of the friction laws was very similar, actually. I think even at the regularized Coulomb sliding law is even a little bit more sea level rise at this point in the run. And if you look to the outlines of the glaciers, this is the middle row, you can see Panaim to the left, not so much differences, but for Thwaites, you can see that the dashed line gives the power law output in blue. The solid line gives the regularized Coulomb law output in blue. Of course, the grounding line in the power law case, so the dashed line is much more retreated already. However, on the grounded side of the ice sheet, the power law is a much thicker ice shelf or ice sheet. So there is a lot more ice in the case of the regularized column. There's a lot more ice advected from the during the simulation from the heavily grounded part over the grounding line to the shelf. So that kind of confirms the notion that the Zuid-Iverson law draws more ice over the grounding line and makes the shelf thicker, thereby makes the grounding line less likely to retreat very fast. Down on the bottom row, you can see some quantifications of the grounding line flux and the buttressing number for Pine Island and Thwaites. And again, Pine Island looks still very similar in both runs at this point in the simulation. But by the way, what you see, the buttressing number is a quantification where a low number means more buttressing. It's a bit counterintuitive, but you can nicely see for Pine Island and also for Thwaites that the buttressing and the grounding line flux seem to anti-correlate, or correlate if you flip the buttressing number around. Basically means that if you, and this is again a chicken and the egg story, if you have a lot of buttressing, you have a large grounding line flux, or if you have a small grounding line flux, you have less buttressing. So this hints towards a relationship in between those two, but I'm still working on theoretical cases with MISMIP, for example, to investigate further if I can make this more substantial. So if you look to the sea level rise curves that come from this, so this is the Amundsen Sea region sea level rise curve for all the experiments. So this is with the mass change rates of present day applied, and also the runs with where I applied a 1 degree warming in the region of the Zuidpool coast. Those are the solid lines, by the way, with the +1, and the dashed lines are the normal simulations without the warming. You can see that they're very similar. Actually, they are. Yeah, I would actually say there's hardly any change at all. So, adding a 1 degree warming in the Zuidpool coast region doesn't affect the collapse in the West Antarctic ice sheet. They are dynamically not well attached, apparently, or the West Antarctic ice sheet collapse is just way more vigorous than the collapse that happens if you warm the Ross shelf with 1 degree. You can do the same thing for the Ross area, and there you get a picture like this. So in the dashed lines, again, the run without the 1 degree warming, so with the West Antarctic ice sheet collapse, but without a 1 degree warming. And you can see nicely that in the first 500, 600 years at the South Coast, not much happens. And at that point, the global mean sea level rise starts to increase from this region, and that is likely, very likely, due to the fact that the West Antarctic ice sheet is collapsing at that point from the Thwaites side. So, warming the Zuidpool coast doesn't really have an influence on the collapse of the West Antarctic ice sheet, but the West Antarctic ice sheet collapse has an influence on the how do you say it, on the projection of the Zuidpool coast with or without the 1 degree warming. So that was very quickly the basal friction and buttressing work that I've been trying to do over the last weeks. I also want to give you a quick outlook into another part, which is the flow factor inversion. So what I basically mean with that is that you can, next to, for example, you can tune friction, or you can tune the ocean temperature to fit your modeled ice sheet with observations, but you can also tune the viscosity of your ice sheet through the flow enhancement factor. And there's a lot of images what you see right here, but these are both spin-ups, initializations with either a super high flow enhancement factor or a super low one, the bottom one, a flow enhancement factor. Just to show you what the power of this flow enhancement factor actually is. So to the left, you can, I plotted the surface or the basal velocities over the surface velocities. So a low value means that the surface velocities are much larger than the basal velocities, and a value close to 1, yellow, means that they are about the same. So that basically gives you an idea about the flow regime of the ice sheet. And at the end of the spin-up, actually, you can see that if you use a high flow enhancement factor, so the top figure of Antarctica, you see that there is a very clear distinction between deformation flow and so the shallow ice approximation or the shallow shelf approximation, which is yellow. So more like a sliding flow, where the velocity does not change with depth. However, if you apply a very low flow enhancement factor, so you make the ice super stiff, you get to more like a figure that's down to the left of the slide, where everything is actually sliding. So there is no deformation anymore, because the ice is so stiff that at every point, actually, except for a few dots in the middle of the East Antarctic ice sheet, that they are basically following the shallow shelf approximation everywhere. So that basically we both run with DIVA, by the way, at this point. But yeah, I mean, you can run with DIVA, but if you make your flow and aspect factor super low, you are actually running with the shallow shelf approximation. So that's the kind of the power of this parameter. And to the right, you can see scatter plots between magnitudes of the observed surface velocities on the x-axis and the modeled ice velocities on the y-axis. And you can clearly see that for the higher flow factor, so the top figures, the modeled surface velocities are generally overestimated, and for the low flow enhancement factor, they are generally underestimated. So what I did is or just to repeat, like the higher flow enhancement factor means softer ice, larger velocities, and this is key for the inversion. Lower flow enhancement factor means stiffer ice and lower velocities, surface ice velocities. And I already have a very well working friction inversion, thanks to Bill and Gunther, that take care of the thickness biases. But there is, at some places, especially close in the MNCC region, still quite a substantial velocity bias, because we don't really tune for that. So I thought, why not let the thickness bias being erased by the already very well working inversion regime that we have already. And then after that's done, let the flow enhancement factor take over to kind of help where the friction inversion cannot do it, to get the flow or to get the velocities into the right shape. And I specifically say let it help it, because I don't want the flow enhancement factor to interfere with the basal friction inversion. So if the basal friction inversion really wants to keep the ice at a certain position because it's too thin, but the velocities are too low, that I cannot say that the flow enhancement factor cannot work against the basal friction in that case to make the ice faster, to flow away faster. So to make it very abstract, it looks like this. The blue lines are the velocity errors, and the red lines are the thickness errors of the Antarctic ice sheet, and in the dashed lines the Amundsen Sea region. And what you're basically looking at right now is after I did a basal friction inversion of 10,000 years, I in steps increased the power of the flow enhancement factor inversion. And the goal is basically to get my blue lines down while not getting my red lines up too much, because that means that my velocity error goes down, but my thickness error does not increase too much. And that's exactly what you see. After 3,000 years, so for 3,000 years, the first 3,000 years, I'm running with not so much power to this inversion. And after that moment, I switched them completely. And you immediately see that the error in the velocities decreases while only allowing the thickness error to increase with a couple of meters. So it's still work in progress, but this is a super nice, I think a very nice and encouraging step that actually the flow enhancement factor can be used to erase kind of the velocity errors that arise from your basal friction inversion. And then this is kind of the last slide, and I'm very almost over time already. So just to show you what happens at 3,000 years, these are moving pictures. We're now almost at 3,000 years into and did you see it? It changed completely. This is the moment that the flow enhancement factor takes over. Your velocity errors, that's what you see on the left, decrease, and a very distinct pattern of flow enhancement factor, invert flow enhancement factor values arise. So that's what's going to be the next steps. So I want to more firmly investigate the basal friction, grounding line flux, buttressing relation, possibly with MISMIP or other idealized analytical settings. And I want to work further on the flow inversion factor, because it's really showing me some good results. And maybe at some point write it up and make a paper out of this. So thanks for your attention, and I'm happy to take questions or discuss either now or after the talks.
Thank you, Tim. Any questions for Tim? Online or none?
Yeah. I have one, Tim. So how do you compare thickness errors and velocity errors in terms of badness?
In terms of, sorry, in terms of?
So how do you compare a thickness error and a velocity error in terms of badness? In other words, I mean, do you do it in terms of absolute velocity error, relative velocity error, and how would you translate those if you have some control over which one you're working harder?
So I mean, this is a qualitative question to me. Actually, I don't have a preference for thickness or velocity. Okay, I like it. I like the thickness to be more in a good place than the velocities because of the grounding line. If your grounding line is at the right position, then it's I like that better than the velocity error for some reason. Yeah, but basically what I do is I just showed you the line plot of the velocity errors at every point, and I didn't include it into the presentation. I made, of course, contour plots to see like, okay, what does it actually spatially mean? So are there places where the velocity error is like diminished completely, and is the thickness error like ever on the whole continent increasing slightly, or are there certain places such as the Bungenstok, for example, that start to be how do you say it, unstable? So yeah, I don't really know how I judge it. It's more like yeah, I hate to say gut feeling, but yeah.
Well, a sort of random thought is that since the multiple is the flux, maybe you could do something with flux errors that somehow merge the two.
Yeah, definitely.
All right. Thanks. Let's move on to our next speaker. Mira Bedard, who's here, and she's going to talk about some ocean work she's been doing. Mira, can you share your screen? Or would you like me to share the slide you sent me? Oh, perfect. And you muted, by the way.
Yeah, can you hear me now?
Yes, perfect.
Okay, let me try and... Can you see my screen here?
Yep.
Okay, perfect. Yeah, I'm sorry I missed the whole morning. I've been dealing with technical issues. And then at one point I recorded my presentation because I thought I wasn't going to make it. And then I made it, but then this presentation had the recording on it already. And then I had to, anyway, it's the long thing. But I'm glad to be here. Yeah, so I'm a research scientist at the University of Washington. So all the things that I'll be showing you today are done in collaboration with the people listed on this slide. So as most of us know, Antarctic mass balance is really strongly influenced by the Southern Ocean. Conditions like winds, moisture content, air temperatures arriving to the Antarctic are influenced by the Southern Ocean, and more directly, the ice sheet is in contact with the Southern Ocean along the underside of the ice shelves. So as a result, the amount of melt that we can expect from the ice sheet depends on the local ocean temperature, which is itself a result of the thermal structure of the surrounding ocean and the local ocean circulation. And then other factors such as surface winds and bathymetry all work together to determine your local melt rates at the ice shelves. So today I'm going to be presenting on some very preliminary findings in an analysis we've been working on to compare the ocean state near the Antarctic ice sheet in both a low resolution, or I guess a regular resolution CESM run, and a high resolution simulation. So first, typical model resolutions, like for example, in a CMIP example, here is, this shows a 1 degree horizontal grade resolution on the left here. And if, there's mounting evidence suggesting that finer model resolution reduces the mean state bias. It improves the fidelity of a wide variety of processes. So specifically, a lot of papers point to the explicit representation of ocean eddies and associated atmospheric impacts that have been shown to increase model scale and reduce the mean model bias. So our analysis will focus on 2 CESM resolution simulations. The details are in this table here. So the low resolution run, we use CESM2 with a 1 degree pop ocean model and a 2 degree CAM. This is a historical run with 3 ensemble members, and it goes from 1850 to 2014. The high resolution run only has 1 ensemble member. It goes from 1850 to 2005, so not quite as long. And the pop ocean model is run at a 0.1 degree resolution, and the atmosphere is at 0.25 degrees. So once I'm done this presentation, I hope to convince you of a couple things. First, that the low resolution ocean has a very persistent warm bias in the subsurface Southern Ocean, and that the high resolution simulation tends to do a good job of reducing that bias. Second, that the low resolution model can still adequately capture some of the temperature changes that have occurred since the pre-industrial, and specifically those off the continental shelf in the Amundsen Sea. And finally, I want to communicate that the bathymetry in the high resolution run is too smooth on the continental shelf, and I'll hopefully have time to get into that. But in any case, our ability to trust the ocean temperatures on the continental shelf near the ice sheet is really diminished as a result of this smooth bathymetry. So first, for a little background, we see the classic sketch of the cross-section of the Antarctic ice sheet. It shows how warm circumpolar deep water with this red arrow here can circulate onto the continental, it may lift up and arrive onto the continental shelf and flow under the ice shelf cavity. And once this relatively warm water enters the ice shelf cavity, it can contribute to high melt rates at the grounding line and cause retreat. This is the mechanism that is likely to explain observed thinning rates over the past 15 to 20 years that are shown here on the right, specifically highlighting the Amundsen Sea region as sort of this key region of change. So you can imagine that correctly capturing the ocean temperature is really vital when modeling the ice sheet, since small changes in the ocean temperatures and in salinity as well in the boundary conditions can cause a significant change in mass. So to illustrate this, I just want to walk through how CESM actually receives and deals with this ocean forcing. So going from left to right, we see that the POP ocean grid, and then from this we extract the temperature and salinity at all these depth levels. We then interpolate these onto the CESM grid, which has equal spacing. Each level is about 60 meters thick. And then these temperature and salinity values are converted to a thermal forcing, which is basically the difference between the freezing temperature at that depth and salinity and the actual temperature locally. And then those thermal forcings are then extrapolated under CESM's ice shelves and converted to melt rates using a relationship between thermal forcing and melt rate. Typically, it's quadratic. So you can see that CESM is very much dependent on the POP ocean conditions that are immediately adjacent to the ice shelf boundary. And if you, for example, were to try and spin up your ice sheet model with an ocean that simulated much too warm conditions, your ice sheet would melt back too far and you wouldn't be able to achieve a reasonable ice sheet configuration. So let's get into some of the data. First, I just want to orient you on how the next few slides are going to be laid out. So I'm going to be showing ocean data that's been extracted at each of these locations, indicated with these blue dots. And all the layout will start with panels at 12 o'clock and then going clockwise around this map. So here we have our first temperature profiles. The colored curves are all showing low resolution CESM simulations. And the one that you should be paying attention to here is the orange curve, which shows the modern climatology. The PI climatology is on there. It's just very hard to see because it's basically directly under that orange one. The blue curve shows a last interglacial temperature profile, but we don't need to focus on that now. It's just unrelated. It's some other work we're doing. So the first thing that pops out here is that there's, right, the black curve shows the echo observations. So the first thing that pops out here is that there's a huge temperature bias in the subsurface ocean in this historical simulation and low-res simulation. And it's really, that bias is really sort of pops out below the thermocline. In some locations, the bias is around 2 degrees, so it's fairly significant, and it's persistent around the entire, like at all the sampling locations. So the problem with this, as I said before, is that if you were to try and spin up your ice sheet model with this particular historical simulation, for example, you'd simply roast your ice sheet and you wouldn't be able to achieve an ice sheet configuration that's realistic. So it turns out that the high resolution model tends to make things a little better. So here we have the same figure, but with a new curve overlaid in purple, showing the ice sheet, showing the high resolution CESM run. And if you just start to go through these panels one at a time and take a look, you'll see that the purple curve is doing a much better job at capturing the subsurface temperatures correctly. So similarly for salinity, same plot, but this is showing salinity. And so we see that the low resolution model tends to make the surface layer a little too fresh and the subsurface is a bit salty. The high resolution corrects this bias in some locations. In other locations, it misses the mark a little bit. So it's not quite as consistently doing a better job like the temperature fields. But yeah, so for example, if you were to look more closely at the location that's nearest to the Amundsen Sea, the temperature bias below about 1,000 meters virtually disappears in the high resolution simulation. Between about 300 and 1,000 meters, the bias is reduced, but it's not perfect. And above the thermocline, the high and low resolution are very similar at this location. For salinity, again, below 1,000 meters, the high resolution improves the bias, but above this, it makes things a little worse. So yeah, it's sort of point by point, but generally that huge bias in the subsurface is generally improved with the high resolution. So let's take a look now at how the high and low resolutions actually simulate ocean changes over the historical period, not just the mean state. So here I'm showing temperature anomalies at different depth levels, 100 meters, 200 meters, 300 meters, so on, down to about a kilometer. So for the low resolution run, this is what I'm showing here is the low resolution. So these are anomalies between the modern conditions and the pre-industrial climatology. So what we see is generally the model just generates a broad warming in the entire Southern Ocean at all the levels. The uppermost ocean warms the most, and that magnitude decreases as you go down in depth. If we do the same comparison with the high resolution run, the story is a little more regionally complex. So you can see that very close to the ice sheet, ocean temperatures tend to be warmer, whereas there are some regions north of this in the Atlantic and Pacific sectors that show patches of cooling. So if we were to collapse this into a single metric by computing the mean ocean temperature in a certain depth band, we get this. So the top left figure shows the high res, and then the other three figures are showing the three ensemble members for the low res. So this is showing the mean ocean temperature in the depth band from 200 to 800 meters, which are depths that are relevant to the ice sheet. Again, the low resolution runs all show a broad warming since the pre-industrial, with magnitudes of anywhere between 1/4 to 1 full degree. And if we take a closer look at just the Amundsen Sea region, it looks like this. So temperatures on the continental shelf in this depth band show warming for both the high and the low resolutions runs. And it's even potentially a bit stronger warming in the high resolution run in this location. If we take the mean temperature of this region that I've shown with the box off the Amundsen Sea coast, we get the following figure, which shows the mean ocean temperature anomaly in that area with respect to the pre-industrial. So all the blue color curves are showing the low res runs, while the high shows the red shows the high res run. And a couple things jump out, but I'll emphasize that here the mean ocean temperature anomalies in the Amundsen Sea are comparable in magnitude in both the low and high resolution runs, which suggests to me that the low and high res simulations simulate a similar degree of warming in ocean temperatures at depths that are relevant to the ice sheet since the pre-industrial. This is particularly encouraging to those of us who are confined to using lower resolution simulations. For example, anyone interested in long paleo timescales where you can't run these high-res simulations. There's a little confidence building that the low res can still capture the same degree and magnitude of change in this particular region. So now if we just want to take a look at the cross-section, in the Amundsen Sea region, this is what we find. Again, these are modern temperature anomalies compared to pre-industrial. These cross-sections go to a depth of about 1 kilometer. So first we see that the high-res simulation actually includes a continental shelf, whereas the low-res model does not have a continental shelf with any retrograde slope. The high-res model produces a patch of warming, that high patch, that really sort of bullseye type thing, of temperatures of more than a degree. And we interpret this as a lifting of the CDW water mass. And then we also see that in the low res runs, there's a warming of about 1/4 to a full degree, mostly concentrated though between 200 and 400 meters near the continental boundary. And in the high res run, we see a similar warming off the shelf in the far field ocean, but up on the shelf, there's a cooling. So in a little bit, I'm going to explain why I don't think we should actually be over-interpreting that particular result on the shelf, even in the high res run. Yeah, so before I move on to that, just one sort of the same plot I'm going to show again, but for salinity. So basically we find that salinity follows a similar pattern to the temperature. There's freshening in the upper layers, increased salinity in the lower layers, and a different result between the high and low res in that particular band of 200 to 400 meters right on the continental shelf. And we can also see that CDW water mass lifting as indicated by that really high salinity patch in the top left figure. Okay, so next I want to explain why I want to caution everyone in over-interpreting the results in this on the continental shelf in this high resolution simulation, especially from the perspective of heat delivery to the ice shelf. So this is because the bathymetry in the Amundsen Sea is essential to how warm water flows onto the ice, into the ice shelf cavities. So here's a figure showing the bathymetry in the Amundsen Sea region with the continental shelf indicated by these the yellow colors. And what you'll notice here are these deep troughs with the bluer colors in the ocean floor. And so there's plenty of literature out that essentially says that these bathymetric troughs are the key pathways to delivering warm CDW water onto in toward the ice shelf grounding lines. So here I'm showing you an animation of the high resolution MIT GCM run at, I think this is run at about 1/12 of a degree. And you can see the continental shelf that's indicated by those tight topographic contours. And then you see how ocean currents are carrying water along the bathymetric troughs inland toward the ice shelf. And then this water circulates along, like through this basin toward the west, and then it often exits along these troughs as well. So it can be a pathway in with the CDW, and it can also, these troughs can be pathways out. So the idea here is that the warm CDW water can be lifted onto that continental shelf, but then the delivery of that warm water to the ice shelf is really contingent on the bathymetry of that location. And unfortunately, it seems that these troughs are not captured in these in the bathymetry of these high resolution runs. So here's a plot showing the bathymetry in this region in the GFDL model up the top, and then below in an earlier version of a CSM 0.1 degree ocean. And unfortunately, it appears that this region's bathymetry is excessively smooth in the Amundsen Sea, which would mean that we aren't going to capture any of these critical pathways for warm water delivery to the ice boundary. I've looked at the bathymetry in this region in more recent high resolution runs, including the one that I've been presenting on today. And this is what it looks like. So it doesn't look like the bathymetry has been changed. So here we have quite smooth bathymetric region here in the Amundsen. So I'm not exactly sure of the details why this is the way it is. After some email exchanges with some of the oceanography folks at NCAR, it sounds like maybe it's related to deficiencies in the bed map data, or possibly in translating the depth to the model levels. But in any case, we're still trying to figure it out. But for now, I think it's worth putting on people's radar that for our purposes and interest in impacts on the ice shelf, we're limited in interpreting anything that is happening on the continental shelf in these high resolution runs, which is rather unfortunate. So finally, for context, I wanted to plot how the new ocean MOM model would represent this region. So on the left, I'm showing the nominal 2/3 degree bathymetry, and on the right, the 1/4 degree bathymetry, and what those would look like in as part of the new CSM3 release. And the bathymetry shows here would be improved representation of these troughs. So that builds some confidence that this issue may be resolved in the next version of CSM3, but for now, It's certainly something we need to consider when we interpret the ocean heat delivery along the continental shelf in this region from these high resolution runs. So yeah, the take-home messages here, again, the low resolution ocean has a persistent warm bias in the mean state of the subsurface Southern Ocean. So that has to be corrected if you're using those temperatures and salinities to force an ice sheet model. And also that we found that this high resolution run tends to really improve on this bias. Next, we sort of found that the low resolution can still adequately capture the local ocean temperature changes since the pre-industrial, especially in that key region of the Amundsen Sea. And finally, we find that this smooth bathymetry in the high resolution run really impacts our ability to trust the ocean temperatures or any of the conditions that are simulated on the continental shelf itself near the ice sheet. So with that, I will end and take questions.
Thank you. We have time for one quick question from you. One was answered in the chat, I hope.
Well, I have one that's sort of related because I'm curious why you use two different versions of CESM for this. The differences in the atmosphere and land and even the sea ice model are pretty significant between the two.
Yeah, it's a good question. So I think that's the only high resolution run that's been done. It's with CESM1. So yes, they're different models, versions, but they're the only ones we have.
Okay. Be surprised that there isn't a high resolution CSM2 run floating around somewhere.
From 1850 to 2005?
Yeah, maybe that was the
Not
issue.
sure there is.
Okay.
Yeah, I just wanted to know what it did to the sea ice. That was all.
I'm looking at that. I'll let you know.
Okay, cool.
All right, thank you. So we're moving on to the next speaker, Filipscom, and to us about glaciers in CESM.
Okay, go ahead. Thank you. I'm going to talk about glacier simulations using CESM specifically for the European Alps. And just as some background in the Earth's glaciers, since we haven't had any other glacier talks today, there are about 200,000 glaciers in the world that have been mapped in a data set called the Randolph Glacier Inventory, or RGI. They're conventionally divided into 19 regions, as illustrated in the plot on the upper left. The circles in that plot are proportional to the ice volume contained in each region. So you can see that the vast majority of the Earth's glacier ice is contained in the Arctic, Alaska, and adjacent to the Antarctic ice sheet. But there are, of course, smaller regions such as the Alps and Rockies in New Zealand that are also RGI regions. Their area is about 700,000, that should be, square kilometers, volume 158,000 cubic kilometers, or about a third of a meter equivalent sea level rise if all of that were to melt. And in the last decade or so, the mass loss rate from glaciers has been about 270 gigatons per year, which is comparable to the mass loss from a Greenland ice sheet. That's a relatively small portion of all the mass in Greenland, but that represents about 2% of the total glacier volume that's currently being lost each decade. And you may have heard about ISMIP, the Ice Sheet Model Intercomparison Project. There's also a glacier MIP, which has been going on since 2015, which is a framework for intercomparison of global glacier models. The first couple of phases of glacier MIP were focused on century scale projections up until 2100. And one of the main results of that comparison for a paper by Marzian et al. Is that with a high emission scenario, RCP 8.5, the Earth's glaciers are projected to lose about 36% of their volume by 2100. But even in an optimistic 2.6 scenario, glaciers lose about half as much volume, about 18%. And the reason for that is because glaciers are already well out of balance with the current climate. They haven't caught up with current warming yet. And so even if there's no further warming, there's a lot more mass to lose. That's illustrated in the plot on the lower right, where the 8.5 is the red curve and 2.6 is the blue curve. And you can see the 2.6, the global mean surface mass balance, which is about negative, about half a meter of loss per year. stays pretty steady through the century, but you continue losing all through the century. Whereas with 8.5, it gets much worse. Regional effects can be different. So the smaller panel in the lower left is a similar plot for the European Alps. And in the case of 2.6, you can see that the surface mass balance actually comes back to near zero by 2100. That's not because glaciers are recovering. It's simply that glaciers are retreating. And as the lower lying glacier ice is removed, the surface mass balance is now only over the colder part of the glacier, and that's why you return to steady state at a smaller ice volume. The current stage of Glacier MIP 3, led by Harry Zekalari, who's been working with us on these simulations, has a slightly different focus. The question they want to know is what would be the equilibrium volume and area of the Earth's glaciers if global mean temperatures were to stabilize at different levels. And the levels they chose for stabilization include 4 past periods between pre-industrial and 1995 to 2014, by which time warming was already well underway, and also 4 periods in the future out over the next 80 years. And so the basic procedure is you bring your glacier model, which is calibrated to simulate the glacier geometry at a baseline date, which is typically taken to be the baseline date of the RGI inventory around 2003. And you do some sort of bias correction. And then you run your models to equilibrium with the output from 5 GCMs that are each running these various historical and future scenarios. So you have, in the end, different models and different repeat periods, several dozen simulations where you can run all the glaciers to equilibrium in all the glacier regions you're running. Most of the models participating in Glacier MIP are global models, and they simulate most or all of the regions on Earth. We're just getting started, and so we've focused on the European Alps, as I'll show below. So what are some of the challenges with glacier modeling? The biggest thing, as distinct from ice sheets, is that whereas for mountain glaciers, we know the extents areas well, but there's not a lot of thickness measurements. So the best way we have currently of estimating thickness for most of the Earth's glaciers is based on a so-called consensus estimates by Farinotti et al., which were published a few years ago, where they used 5 glacier models to invert for ice thickness with some sort of ground truthing based on actual thickness observations, but also based on the surface topography and various ice flow dynamics principles. And what pretty much all glacier models have in common is they compute the surface mass balance in some way, typically with a positive degree day temperature index or some similar method. But where models differ a lot is in terms of how they handle glacier geometry. The first generation of models used volume area scaling relationships, where if you know the area, you can sort of take an educated mathematical guess about what the volume should be. But these methods have pretty large errors. So the current generation of glacier models, including OGGM, the Open Global Glacier Model, and GLOGEM Flow, they typically have a flow line model of the ice dynamics using something like the shallow ice approximation represented in 2 dimensions, x along the flow line and z. And then you have some sort of parameterization to represent the 3rd dimension across the width of the glacier. And then the more advanced method is to use a 3D model, similar to what we use for ice sheet modeling. But in the past, this has generally been done for a small number of individual glaciers, not for entire regions. So the main innovation in using CESM for a region is that we're extending this 3D approach to an entire region with thousands of glaciers for the first time. So CESM, as you're, I'm sure, familiar with by now, has been used mainly to model the Antarctic and Greenland ice sheets, as illustrated by these velocity plots. To turn into a glacier model, the biggest challenge is that to model glaciers, you typically need a resolution of 100 to 200 meters to resolve individual glaciers, as compared to a typical resolution of 4 kilometers that we use for ice sheets. So 20 to 40 times higher resolution can be a challenge computationally and in terms of numerical stability. Also, simulating the surface mass balance on these small mountain scales with the complex topography and orographic forcing and shading and things is harder. And also for glaciers, it's really important to get the initial state correct, because what's going to happen in the next few decades is obviously very sensitive to what the shape is right at the moment. So I'll talk a little bit about how we have tried to overcome these different challenges. So we're starting with the Alps, which is a fairly good reason to start with, since it's not too large geographically, and it's very richly sampled because lots of glaciologists are from that region historically. And Summer Manala, a postdoc who's working on this project, has been taken the lead in assembling the data sets and developing the workflow for simulating glaciers with assistance from Gunter. And so the idea is we get the glacier outlines from the latest version of the RGI, version 6. And then Summer was able to create a glacier surface and bed elevation / thickness data set by merging USGS surface DEM with the Farinoti thickness estimates that I referred to. So that allows CESM to read in an input value of the thickness for all the glaciers. And then our atmospheric forcing, there's two fields that we rely on, the 2-meter air temperature and the precipitation. We use monthly means, and we get these from a global ERA 5 reanalysis data set called W5E5 version 2, which has been bias corrected, and the GCMs that Glacier MIP 3 uses are bias corrected in a similar fashion. So that allows us to use the same data set for spin up that we're going to be using that's been used to bias correct the models that we're going to be using for forcing later on. So to compute the surface mass balance, we're using a temperature index method, which is a little different from what other models have used, but similar in concept. We have a 2-equation scheme where the 2 equations illustrated as 1 or 2 express 2 different ideas. Equation 1 says that when the climate was in balance sometime around the 1980s, before global warming was as strong for the Alps, you had a net mass balance of 0. That's the 0 on the right-hand side. And so, you have precipitation leading to accumulation, and you have melting due to temperatures being above a melt threshold, which is taken to be -1 degree. And this equation represents a sum over one entire glacier. And the second equation says, well, when you go to a warmer climate, which in this case is 2000 to 2019, then you're going to have most likely a negative mass balance. And in this case, the mass balance on the right-hand side comes from a recent data set by Huguenet et al., who computed the decadal scale surface mass balance for all the Earth's glaciers. And the P prime and T prime there represent the warmer temperature and precipitation. So we solved this equation for every glacier, summing over monthly means to get an annual climatology, and doing this for every glacier. And we compute unknown factors alpha and mu, where alpha is the precipitation correction factor of order 1, and mu tells us how much melting we can expect for degree of temperature above the threshold. And beta is sort of a subsidiary correction we use as necessary, but typically is 0. For our dynamics, we're using the depth integrated higher order solver that we typically also use for the Greenland Antarctic ice sheets, which includes the different stresses of interest that are not included in the shallow ice approximation. And one of the great things about this scheme is that it's fairly efficient and also very stable at high resolution, unlike the shallow ice approximation, which for numerical reasons is highly unstable at sub-kilometer resolutions. And for basal friction, we're doing something similar to what we often do for ice sheets, whereas we have a power law and we have a parameter called CP, which we take to be a tuning parameter, and we nudge that parameter to make the ice flow faster or slower as needed to get a good match to our target ice thickness, which is taken from the Farinoti data set. Adjusted, however, we make our target a little thicker than the Farinoti data set because Farinoti is from the RGI date, and we want the ice to be to correspond more to the baseline about 20 years before the RGI date. And then the other tricky thing about simulating glaciers with CESM is that we want to preserve glacier outlines to the extent possible. We want a given glacier to maintain its identity with just modest advance consistent with a cooler baseline climate. And it's impossible to prevent some spurious advance due to just diffusion in the advection scheme, and also the fact that there's some regions that don't have snow in reality, which are very high and cold and steep, and the model wants to put snow there. So that happens to some extent. But we, at any rate, we track glacier advance, and when a glacier advances, we give the new cell an integer ID, which is the same as the ID associated with the original cell. And if a glacier retreats, we set its ID to 0, but if it advances again later on, it retains its original value. And if we have an advanced cell, if it's in the ablation zone, we allow it to melt, but if it's in the accumulation zone, we ignore the SMB and don't allow it to grow. And that helps discourage spurious expansion of glaciers outside their original outlines. And to spin up the model, it turns out that it takes about 10,000 years before you reach a very stable glacier state. So we do that for 8,000 years, inverting for this power loss C and other parameters, and 2,000 where we just hold the parameters fixed unless things relax. The two plots with the yellow on blue show the glaciated grid cells within the whole Alpine region, which includes Switzerland and Austria and a bit of Italy and France and other countries. You can see that between our 2003 state that we start the run with and our baseline climate, the glaciated area remains very similar, though there is some expansion. And then the three plots at the bottom show the initial ice thickness, followed by the difference between the final and initial thickness. And on the error scale there is 50 meters either way. So you can see that for the most part, our errors are within 50 meters of the target. And the places where we have expansion are typically areas where we want expansion, like our glacier termini. For example, this terminus here of the Aletsch Glacier in the Swiss Bernese Alps is a little beyond where it's observed today because it was in fact farther advanced in the 1980s. And then the lower right plot shows velocities. So a little hard to see at this scale, but the maximum velocities are about 500 meters per year and are found in the largest glaciers in the Bernese Alps. The Matterhorn is around here in the Pennine Alps, and then Mont Blanc, the highest point in Europe, is in the Mont Blanc Massif, illustrated in the lower left. So zeroing in on some specific regions, this is Mont Blanc. The photographs here are taken from a cable car that goes from the L'Aiguille du Midi over to the Italian side of the glacier, directly across the upper side of the Mer de Glace, which if you're ever fortunate enough to be in this region on a clear day, I highly, highly recommend. It's absolutely stunning. At any rate, so these photographs are taken from that cable car. This is looking up the Mer de Glace toward the summit of Mont Blanc. And then the other one is taken from the same location looking down, and you can see where the Mer de Glace kind of goes around the corner, and then it's around to the left, it descends into its valley, into its ablation zone. And that's illustrated in green on the panel here on the left, which shows the Mer de Glace and several other glaciers at the end of the spin up. And for each of these glaciers, the shape is pretty well preserved. I'll just point out in the Glacier du Trian here, there's a blue patch which shows where ice melts in our spin up. The reason for that is because our SMB parameterization doesn't take into account aspect and shading. So in reality, this is a north-facing shaded slope, but the model doesn't know that, so it thinks the glacier is warmer than it really is, and it melts the ice there. And there's a certain part of that that's unavoidable unless we had a more sophisticated SMB scheme. Similarly, for the Bernese Alps, we have the Jungfrau Glacier, and here's the Aletsch Glacier simulated here. And again, we preserve the glacier shapes pretty well. So we spin up the model, then we do a commitment run where we hold the climate fixed relative to 2019 and see what happens. And the news is not good for the Alps. Even with no further warming, which is a highly optimistic scenario, the Alps will lose more than 60% of their 1980s volume, with most of that loss coming within the first 100 years, illustrated by the plots on the right. Compared to other Glacier MIP3 models, and then Lillian Schuster, who's doing that analysis, provided these plots, CESM is actually more sensitive than most of the other Glacier MIP3 models that simulated the same region. The CESM is illustrated by this brown curve here, where qualitatively the behavior is similar to the other models, but we come in about 10% lower. So where most of the models are losing 60% of their ice in the Alps, we would lose, let's say 70%. And so one of the things we'd like to understand in the future is why CESM is more sensitive than the other Glacier MIP3 models. It's likely related to our 3D geometry, because these other models are that are somewhat less sensitive have 2D flowline geometry, but we'd like to understand that in more detail. It may be that CESM has some glitch we haven't interpreted yet, but it may be that it's actually more realistic because of the 3D geometry. We would definitely like to extend this work to other glacier regions. So summer, we'll be focusing on high mountain Asia. And if there's anyone interested in the community, this would be a great tool for investigating glaciers in other regions of the world. Although we do need to add support for marine terminating glaciers if we're going to do that. And finally, volunteer already.
Nice. Back there.
And finally, something else Summer's looking at is incorporating dynamic glaciers in CESM. CLM now has a mountain hill slope scheme, which might be a really great tool for incorporating some of these more complex aspect-dependent factors that are ignored in the simple SMB scheme. So thank you, and I'd be glad to take any questions. All right, time for question 3.
Yeah, so I'm wondering if the connection to CLM, is there basically the glacier mount that goes away, where does the water go? Is this hooked up such that you can test the effects on the land scheme, or, you know?
We can. It's similar to ice sheets, where we can make the ice sheets evolving or non-evolving.
Okay.
And if we put in a CESM grid, which corresponds to a glaciated region instead of, as compared to an ice sheet region, the water is basically being treated in the same way. We can compute a change in mass due to surface mass balance changes, and then have that water run downhill.
Perfect. So it can run, and that's captured all the way down.
Well, we haven't actually done it yet.
Okay.
but in principle, yes, we should be able to do that. And also something someone would like to do is take the output and apply it to regional hydrology models. And that's something you don't need CESM for. You can use offline CESM and generate runoff that then you could feed to a hydrology model. And that's one of the great things about tracking these individual glaciers at a small scale, is you can get actual information about how much the flow would change going into a specific river on a decadal scale.
Perfect, thank you.
CESM uses the RTM river model. So most of the CESM water runoff goes through CLM to the river model. And so that would be what sends everything to the right places.
But was there a question online? I heard a boom previously, but I don't see a hand raised.
I think I saw somebody compliment how nice it was, the talk.
Okay. All right.
Looks
Yeah,
really.
it wasn't a hand. It was a compliment. It looks really cool.
Can I ask a question?
Sure, quick one.
Yeah. How do you think it's easy to incorporate marine terminating, lake terminating in your study? Because framework, I've been studying the Southern Patagonian ice field, modeling the past, predicting the future, and it would be nice to apply this exercise on that ice field, though. But the difficult thing is that on the east they're terminating in lakes, and on the west they're terminating in the Pacific Ocean and fjords.
I don't know if it's easy, but I'd love to talk with you about it. Maybe we can brainstorm.
Okay, cool.
Right, thanks. So let's move on. The next speaker is me. And I'm going to give you a quick update on CESM and CSM3, with a future version of CSM2 that's being worked on right now. And the first thing to know about CSM3, who is a global corporate model, is that people use a model, but sometimes it's unclear what goes behind it, and there's countless hours of decision making that goes behind creating a model that takes a lot of effort. And the little word that I've put in there is just a small fraction of decision that we have to talk about and or prioritization or configuration to implement. So it's very complex. And so right now we're spinning the wheel to make a delivery of a new version of CSM. Towards CSM3, this is a quick timeline, and pretty much what this says is that as soon as the new release of the model is done, the work toward the next release pretty much starts. And CSM3 pretty much started not too long after release CSM2. So today we are on February 2024, and can you see my cursor? No, of course not. Okay, so we started bringing, the way it works, a lot of the model component do their own development and improvement, and eventually the goal is to merge them together and to have a coherence answer when they communicate to one another within the current model. And since March, maybe slightly after March, we started this process, and right now we're actively working on creating a pre-industrial control version of the model, and have the model component get in equilibrium with one another that leads to an acceptable set of deployment then. The plan is in the summer of 2024 to create what we call a science freeze, where we're not going to change the science of the models themselves, so that we can then perform some tuning, update some forcing, do some testing, document and run some simulations before releasing CSM3, hopefully by winter in 2025. So where does the land ice working group sit into all of this? Land ice does matter in a global climate model. Even though we might not be the biggest component, we are the troublemakers. So right now, and I'm going to talk about it a little bit after, but we had some surface mass balance biases in CSM2. So what we're trying to do right now, what we're going to work actively on, is to try to diagnose any surface mass balance in the PI controls that are being performed, experiments that are being performed right now, so that we could then create a good initial state for CSM for the Greenland and Antarctica ice sheets. What's a little bit tricky here is that, for us to create a good initial condition for the Greenland ice sheet, we need a good PI control simulation first. So it's like, hopefully they get something good for us before the science freeze. So we are also, as Mira just showed you, we need some good ocean state in the Southern Ocean, because the plan is to add Antarctica to CSM3, and if the ocean is not in a good state, then Antarctica is not going to like it. So we're going to do this analysis along with the surface mass balance analysis and try to diagnose any biases, and hopefully that we can improve the model on this end. We're going to, starting soon, we're going to start implementing the one-way Antarctica ice sheet coupling. And by one way, I mean similar to what was done with the Greenland ice sheet, where right now you have coupled feedback between with the atmosphere and Greenland ice sheet, and Antarctica requires both coupled feedback with the atmosphere, but also with the ocean. So we're going to start with the atmosphere and then include the ocean, one step at a time. Once this is done, we can then move on to develop the two-way Antarctica ice sheet coupling mechanisms. And here's the mechanism, because it might take a longer time to diagnose like a good scientific version for evolving Antarctica. So the mechanism means like all the processes will be in place, and that Antarctica will be able to receive all the signals from the forcings from the ocean and the atmosphere, and a signal back. We're going also, the plan also to add some paleo ice sheets, such as the Laurentide ice sheets for LGM or less interglacial simulations. And before moving to the next slide, one of the questions I added on the bottom arrow after winter 2025 is whether we need to add a topography updater for the Antarctica ice sheets. So what this is that, as you may know or not know, right now, the ice sheet doesn't talk directly to the atmosphere. It takes all of its information from the land model. But when the, for example, the Greenland ice sheet loses a lot of mass, it changes its elevation, and this information needs to be sent back to the atmosphere so that it could adapt to this change in elevation. And this is very important for long-term simulation or even century timescale simulation of the Greenland ice sheet. Now, the question is this important for Antarctica as well? And this is something that we're going to need to talk about. It's definitely important for paleo timescale simulations, but for century timescale, we need to determine this. And along this line, we're also going to work on some diagnostics, and that is going to tell us more about this later.
Can I ask a question before you move on?
Sure.
Because it's developed a two-way Antarctic ice sheet coupling mechanism. So will you let Antarctica, the way the atmosphere and ocean seas it decrease? Is its geography going to change? And how will you do that? Because that's a challenge.
I'll get to that.
Oh, okay.
So this is a little bit of a history of what happened in CSM2 regarding the green surface mass balance. What you're looking at here is a CESM simulation of the surface mass balance in CSM2 compared to original climate model, RACMO. And you can see in CSM2, so we had a good comparison. These are average between 1970 and 1989 for RACMO, and this is an average from 1850 for CSM. So the agreement between both is very good. You see some narrow southwest ablation zone in CSM2 that could be due to early time period. And in this configuration, CESM is not evolving, so the ice is not added where there's no ice originally, but CLM can form ice over bare tundra. So some cause of the biases that you can see, especially in the north, is that snow is surviving winter, which is one cause of it. In the south, there's a little bit too much snowfall in the interior, which is very resolution dependent. When we tried the same comparison on a quarter degree of the atmosphere, most of these biases disappeared. So from private conversation with Dave Lawrence, he mentioned that snow physics have been improved and the soil temperature in CLM are better representing what's happening in Greenland, which might help alleviate these biases. On the Antarctic side, we have similar stories here with some biases. What you're looking at here is a picture from Dunmire et al. 2022, who looked at surface mass balance biases in Antarctica. She did this with Jan Leenaerts. Overall, the reconstruction is based on the MERA2 data. And what you can see is that overall CSM2 has a good representation of the spatial pattern, but it's bias high, and this high bias is represented by the time series. You can see on the top image here, where you have the mean surface mass balance state from CSM2, the large ensemble, compared to CSM1, but you have the mean state in error bars on the far right of the graph that can be compared to the reconstruction. So CSM2 in Antarctica for surface mass balance is biased high, and this bias is stronger along the coast. But based on this picture, that we can zoom in, like for a region that's of high interest to us, as Mira talked to us before in the Amundsen Sea embayment for Thwaites and Panama Glacier, this bias doesn't seem to be too strong. So what's important to not have too much high biases in average is that this way we don't have to try to find mechanism to reduce the artificial thickness that is due that would come from this process. So all of this analysis now, in the next few weeks, we're going to start doing it again, but with CSM3. Now, spinning up Greenland within CESM, this is just a process to explain to everybody how we plan on doing this. So what we first do, we start from a CESM standalone initialization and this is done by using bed topography and ice thickness right now from Bed Machine version 3. There's a product created by Matthew Morningham. We take some geothermal heat flux for the Greenland. It was from Matos 2017. In CSM, we remove the ice shelves in Greenland. We do this because right now the Greenland ice shelves are small. They're not as important as in Antarctica, and that's something we're going to improve on in the future. Our configuration, we work on configuration options. Grid resolution is 4 kilometer. We do some inversion for basal friction for the historical and future runs, and we use pseudoplastic as a basal friction law, or as we improve on it, as we do more testing, we might use a new hydrology scheme for paleo Greenland ice sheets. Once this is done, so once this configuration is done, we then start running with CESM standalone. We use the SMB and air temperature from CESM and do the inversion of the basal friction parameters. When all of this is done, what we're going to do, we're going to add this into CESM and then force in a fully coupled configuration Greenland and with the physics that's in CSM. We're going to do this by running the carbon model for chunks of 30 years with an accelerated CESM of a factor of 10 to reach a faster equilibrium. And within this process, we're going to also update the topography if needed. On the Antarctic side, we're going to follow a similar process in terms of initialization. This one, we don't contain ice shelves, and we're going to use summer forcing observation to do the inversion process. And we're also going to include some calving masks. So the problem with Antarctica right now is that we don't have a good calving scheme that works well for future scenarios. And so what we do is that we restrain the advance of the calving front to a calving mask beyond which CESM calves the ice. This could be problematic, especially when for longer time scale simulation, like paleo climate simulation. But when we know that the climate is warming and the Antarctica is retreating, it has limited impact. Once we set up CESM, the goal here is to be able to run. We're going to run CESM as a standalone and to do a PI control using summer forcing correction. As Mia showed us, the bias is kind of constant over time, which gives us some confidence that we can do bias correction for the summer forcing, for ocean summer forcing. So what we're going to do this bias correction is to use the observation that was derived for the SMIP6 project by Zahler A.C. Davis, take a modern climatology of the state of CESM and then create a correction by taking the difference between the observation and the climatology. We would then add this correction to any pre-industrial state before evolving Antarctic further. And then once we do this, again, we would put the Antarctic CESM representation within CSM and evolve Antarctica with a similar process. At first, because as Betty hinted at, POP doesn't have an evolving coastal area, and the ocean boundary remained fixed, which is no longer the case with MOM6. And so at first, because this is really new, we're going to keep those coastal area fixed before then working with the ocean working group to have a version that can evolve these coastal areas and adapt to the retreat of the ice shelves in Antarctica. As CESM is concerned now, for the CESM standalone, we plan on having an intermediate release of CESM, which we call CESM 2.2, which will be able to be merged with the beta tag of CSM3. There's going to be new ice sheet physics, the new Coulomb-basal sliding law that Tim talked about. There's Zoid Iverson, which is fully operational right now. There's going to be a flux routing basal hydrology scheme, which is operational and requires a little bit of testing, but it's almost there. subice shelf cavity ocean temperature and salinity interpolation. It's working just great. Some acid initializations, typical spin-up as we've always done, or one that includes a change in thickness rate that Tim van der Acker worked on. We're going to have test cases for Antarctica and Greenland that now just need to be tested in Portland and derecho, and lift kit, which is a code validation kit. And for CESM3, the mountain glacier will be incorporated. Bill just told us about it. And we're going to try to include some new Kelvin schemes, subice shelf cavity circulation, and have some tools and data set for diagnostics and grid generations on top of documentation. So this is it for me right now. This is our contact information as always, and I'm just going to say that it would be great to see all of you in person if you can this summer at our CSM workshop on the week of June 10th. So thank you very much. And any questions?
Three has questions.
Sorry, they're all in the chat. It was just about the VR simulations, if there's any testing being done with variable resolution grids, just to make sure that you don't blow up the, I mean, like, I'm assuming most of the testing is with the finite volume core, for example, and.
So right now it's a spectral element grid that's going to come in CSM3, and right now
it's going to be standardized with spectral element grid?
Yes, at the workforces as well.
Well, the challenge is that the Arctic kind of got a free ride with finite volume because we got higher resolution there, but by meridians coming together. But for the SE grid, that doesn't happen. So a 1 degree grid is a 1 degree grid in the Arctic as well. So all of our resolution dependent biases could be worse.
So is there testing going on? I mean, there was biases in the spectral element grid, the variable resolution that I'd worked with in Antarctica, and Greenland seemed to be better, and Antarctica it seemed to be worse. So I was just worried that, you know, whatever improvements would be made would just kind of kill the variable resolution. And that's not just the spectral element grid. That's about the enhanced resolution.
So is there work going on? I think.
Oh, the paper's published.
Yep.
So I mean, we can talk about this separately, but it's just if you know we're looking to do enhanced resolution in the future around Antarctica, it's not behaving the same as Greenland, and so what I was hoping is that you know, just to be able to use that, because it is useful for a lot of other things, is that, you know, that a lot of the testing could be done to just make sure that maybe, you know, it's not just getting better in the 1 degree, that in the 1/4 degree, that it's also improving. Anyway.
Yeah, that'd be something to ask Adam. I think right now we're not even to that point in the PI control, but I assume Adam's going to look at it carefully.
It's a good point. I'm sure Adam knows.
So I have a question for you of something I was asking during the break. And I was looking at what we did, Aliyah and others, when we did the last interglacial. And I thought we downscaled to the CESM grid with a 1 lapse rate, 6. But think of what Maren said about seasonality. Is that going to be included where we can look at seasonal?
We don't, at the moment, we don't support a spatially or temporally variable lapse rate. We could, if we had, you know, data or model runs that we could use to base the parameterization on.
There's Maren raised her hand, so she can clarify for me.
Go ahead, Maren.
Yeah, so it is different when we are talking about the dynamical topography at a 1 degree resolution, and that when it is two-way coupled, we can have this seasonality. But then the downscaling is through the elevation classes, and it is with the fixed 6 Kelvin per kilometer. Yeah.
Yeah, I actually made a note while Gunther was talking, because I think that when we make that change, a lot of times it's with a source mod that we added in for the ISMIP runs. So it's one of those changes that you had to add in for the variable resolution to replicate the ISMIP 6 runs. And we should revisit if we want to try to bring that in for CESM3, but I don't know that the CLM people were particularly happy with the idea of a fixed lapse rate like that. I think they like having the variable lapse rate that is default in CLM. So that's going to be a discussion probably.
And for paleo, it's kind of important. You think of the last interglacial, it's strong summer anomalous forcing, not winter, so it's not anomalous all year round. It probably averages out close to zero, but the feedbacks could be important.
All right, thanks. Let's move on to our last speaker, Kate.
Hey.
About software engineering update.
Yes, I'm going to go pretty quick because I know we're all probably pretty hungry and I don't have a lot here to talk about. So this is going to be mostly about the work that we've done over the last few months, which has involved a lot of porting to Duratio and support for the new computer with CESM and CESM, but some also talk about diagnostic efforts, and then I'll mention some of the other things that we've got going on too. A lot of these software engineering talks don't have a lot of cool visuals. I don't have tons of maps of ice sheets, so I actually asked DALL-E to help me. So this is an AI image generator to produce the images for my talk. So you can see on each of these slides, there's a prompt that I use to produce this image. So this is what an AI thinks that a glacier scientist at work looks like. And to be fair, I wasn't very clear if it was a human or a robot glacier scientist.
That's not a real glacier with a mountain in the background. That's just.
Nope, this is all AI generated. Apparently latex gloves and a helmet are very important for glacier scientists.
This is awesome.
Okay, so Duratio is the new supercomputer that was brought online late this fall for NCAR, and yeah, it's been a fun challenge and a lot of work going into porting all of our models over. This is a bigger machine. It has more GPUs, and there's definitely going to be, well, there's already pushes amongst the CESM scientific committee to try to utilize those GPUs further. So you guys will probably hear more about GPU work with CESM in the future. A lot of things are similar, but there's new compilers and a better Python system, I think, in this new model. So yeah, this is my image of a glacier scientist working with Duratio. You can tell because he's got the parka and the glacier behind him, apparently. So
Aren't there like young women who are glaciologists too? Oh, okay.
So yeah, the Duratio overview. There's some documentation available online. It's not the best. I have a link to the documentation that we've built for the Land Ice Working Group in here later. But I wanted to point out that if you haven't started using the new machine yet, if you have access to our allocations, that those are available, and there's plenty of allocations there. And that Duratio users typically see 1.3 times improvement, so you actually will use fewer core hours for working on Duratio than you would on Cheyenne, according to the documentation from CESL. So here's the link to the Land Ice folders, and the CESM standalone now supports building and testing on Duratio fully. So if you use those tags, CESM made 2.1.013, which I've linked here, you should be just fine running CESM standalone on Duratio. And yeah, this is a glacier scientist. You can tell because his eyes are glowing and he has a air tube. Or she, I guess this isn't, we don't know. So building and running is very similar to what you have on Cheyenne, except that Intel is now the preferred compiler. So we've added some updates to CESM to try to improve the build and runtime, which I think have been pretty successful if you use the newest tag there. One of the things that people need to be aware of is that the nodes in Duratio have 128 cores, which is a large increase from 32. So when you request nodes on Duratio, realize that it's going to have a much larger parallelization per node. And then the queues also have different names. There's no more economy or share queues. There's a developed queue that can be used, but has more strict limitations on it than the economy or share queue did before. Also, I'm sure most of you have heard that we need to all move from the Glide P workspaces. So the new workspaces Scratch from Cheyenne is still available as read-only. Now we need to use Glade Duratio Scratch, so you may have to update your scripts to look at the correct Scratch space, and that the new group workspaces are all on Campaign. So I think most people have successfully moved from Glade P to Glade Campaign, but if you still have data sitting out there, it should be read-only right now, and this is, the end of your last chance for that. So CSM also has been ported. We ported all of the release tags that we've had so far. The best option, if you have a version of CESM that you want to use on Duratio, is to use the most recent tag. So the Duratio supporting CSM tags. And this is also updates for some GitHub changes that have happened. So you may get manage externals errors if you don't use the most recent tags. So for the 2.1 series, it's 2.1.5. The 2.2 series has a 2.2.2. And the CSM 2.3 Alpha 17A has all of the Duratio and managed externals support in it. So if you have trouble updating, and it's true that if you move to Duratio or update to a tag, this could change your answers just because of the differences in compilers and machine structure. So if you are very sensitive to those sorts of answer changes, please contact me and I can help you with other methods for updating to support the new machine. And I like this heroic glacier scientist because she's got some, I think, glowy stuff on her.
No, who's up with these fabulous outfits?
I'm telling you, yeah. And also the long hair is very important, apparently. So another improvement on Duratio is that the Python environment is more integrated. So previously Python was a little build your own on Cheyenne, but now Python 3 is the only supported Python libraries on Duratio. Conda is a module that you can load, and there's a in-car Python libraries NPL module. I guess it's a Python environment that is curated by Sizzle. So it's kept updated with the most recent and all working together Python libraries, which is really nice. So there's some Python and Conda documentation online you can take a look at. And then also Jupyter Hub works on Casper and Duratio, similar to Casper and Cheyenne as previously. This guy is extra cool because he's got more goggles. That's important. All right, we've also been working on diagnostics pretty seriously. The goal is to have a diagnostics package for the CESM release. This goal is simple to run, a comprehensive view of Greenland or Antarctica separately or together over the course of the run. It needs to be a first look package so that we can check for possible issues as the run proceeds more than anything else. I don't want to do CMIP runs again without checking photography, updating each time, because that was very difficult last time. And we'll be looking at model run versus another run and model run versus observations, but this isn't the sort of thing that's going to produce papers. It's for preventing issues like Alea's albedo problem that she had in her run too. Just trying to keep an eye on everything as we go. But the to-dos involved in that in the near future involve adding an option for history output that's more in line with CESM and building up these diagnostic notebooks for the pictures that we want. And yeah, this was the AI's version of a scientific diagram of Greenland, which I thought was pretty great because of the teeth here. I don't know if you can see. Yeah, got teeth and legs. So you guys, I think your jobs are safe. You're not going to be replaced by AI anytime soon. There is a big effort to build a CESM unified post-processing diagnostics package called Cupid going on right now. It started the beginning of this year, led by Mike Levy and I just totally forgot her name.
Tegan.
Katie Tegan. And yeah, there's a lot of work going on in this. So our goal is definitely to integrate with Cupid and to leverage as much of their code as we possibly can so that we're not rewriting or reinventing the wheel, as it says. We definitely want to maintain this compatibility with all of CESM so that our packages are working with that. Yeah. And one of the things that I've been working on so far this fall has been to port BATS and LibKit up to Duratio as well. So I don't know if any of the LibKit guys are online or around, but they will be seeing a PR from me very soon because we have BATS working on, oh, I gave a bad link there for LibKit. But, oh, no, I see what I did here. So the first one is my fork, KTC BATS. That's my forker BATS, and that one has the branch that is working on Duratio. So if anybody wants to use the build and test system for building all of the CISM tests at once, that's where the Duratio working version is. And then the main repository is the next one that I will try to integrate my changes with, if they'll let me. And then the next will be the port for LibKit. And the goal is to have this available for CSM3 development as Bill and Günther continue. So this is my last slide. I'm finishing up. Basically, the negative water flux work is still going on, and I'm definitely want to have that done for CSM3 before the freeze this summer. I continue to work with GHub, and one of our goals there is to have the version of CISM that will run on their website so that it can be used as sort of a tutorial and interactive version that we can submit and use the University of Buffalo resources. So if people don't have access to a supercomputer, they can still run CISM. And this might be really good for educational work with undergrads or, school students who don't have access to our big supercomputers. So that's what I've got right now.
Thank you.
Do you guys have any questions for me? Thank you. I can add these two. I thought I knew that woman. I don't know. She's so familiar to me.
Yeah.
Doesn't she?
No, she totally does. Anyway, sorry, I'm obsessed with the picture.
Great. Okay.
No questions for Kay? All right, then. Thank you so much, everybody, for attending, for joining us and staying longer, going on the lunch break. So we will see you all very soon. Hopefully see you in person in the summer. And for some of you, see you in a couple of weeks, actually, online to our monthly lenders meeting. So thank you, everybody. Have a great evening and great day.
Thank you.